Thank you all for joining. Today we have a tutorial on GPU-based acceleration for deep learning. I think the program is quite exciting, and we have 4 experts in the field. And what is more important is that what we would like you to take out from the tutorial is learning about the GPUs, learning about hardware for deep learning, learning about GPUs, but more importantly, learning how to maximize the use of those GPUs from training to inference. And for that, we will have talks about how the hardware works, what are the tools available out there for profiling the networks, for understanding what is happening in the hardware. And then we will have a specific software tricks that you can use for maximize the GPU utilization. And in the second part, Main and Danny will talk about recent progress on how to maximize compute on the edge. And if everything goes well, Main will also give a live demo of how can you actually bring high-performing networks into an embedded platform. So we're going to start this tutorial with the first presentation. Jason Clemens will give the first presentation on foundations of GPU architecture and from a hardware perspective. Jason is a senior research scientist at NVIDIA. His expertise is in mobile computer vision. And at the moment, he's working in the intersection between machine learning and computer architecture. Please welcome Jason. He's remote, actually. So Jason, you want to go ahead and share your screen, and the stage is yours.
All right. Can everyone hear me?
Yeah, we can.
All right, excellent. So I tweaked the title without telling Jose just a little bit. Foundations of DL hardware. It is with a focus on GPUs. As Jose mentioned, I'm an NVIDIA researcher. I work in our architecture research group. Thank you for the introduction, Jose. One of the things about hardware for a DL, which is interesting, just hardware in general, is that hardware systems kind of exist on a continuum. On one side of this continuum is this idea of general purpose, CPUs, GPUs, things that are programmable. You can do whatever you want to do with them. As you move further to the right on the spectrum, you end up with things more like fixed function. These are things that do one thing, but they do it really, really well. These are custom chips. They are very fixed. You can't change what they do. And it turns out most of the systems we use for DL, actually all the systems we use for DL, are somewhere on the spectrum. The left side, as I mentioned before, CPUs, very programmable, very flexible. You can do whatever you want. GPUs, very programmable. They are a little bit more special purpose. They're more like application-specific processors. GPUs are designed originally for graphics processing. Now they're for just any type of processing where you have a lot of parallel math that you want to do that looks very much GEM-like. Then we have things, you've probably heard of them, if not by the name systolic arrays, maybe like the Google TPU, but these are systems that are basically designed that are a little bit less programmable. They are a little bit more fixed function, but they're still application specific. They still have some capability to do an array of things, just maybe not as programmable as the CPU or GPU, and a little bit more restricted in how they execute to get efficiency. Then we have things like application specific accelerators. These are things like NVIDIA's DLA, any type of neural network accelerator. If you Google Scholar deep learning accelerator, you see a bunch of things, Iris, Simba. These are things that are designed to do a specific application, and they're an accelerator, so they're not exactly fully programmable. They are more configurable, is the way we typically say. And then you finally have the ASICs, which is application specific integrated circuit, which is basically the ones that are more fixed function. And as you note here, as you move from fixed function to general purpose, you get more flexibility. But there's another piece to this spectrum that we get concerned about, which is the efficiency that happens. And what happens is typically, in order to be more general purpose, you give up some efficiency. So in order for the CPU to be able to do everything and be used for everything, it's not as efficient at certain things. In particular, graphics, which is why we have GPUs, right? We found that, hey, we want to do a lot of compute. We want to do it well and efficiently. GPU became a specialized system. Systolic arrays. And then if you move further to the right, you get to the efficiency when you start saying, hey, this is a configurable accelerator. This thing does that acceleration of that task and that task only. And so you get very efficient because you've kind of jettisoned all the inefficient components. And then you end up with the ASICs, which are just, they do that one thing, they do it well, You're not really going to find anything that's programmable or configurable that will do it much better. And there's this tension as you look at the hardware system you're trying to deploy. You know, you have to decide where you want to be. Do you need to be very, very, very efficient, or do you need some flexibility in your deployment? So let's talk a little bit about these individual systems, or some of the core ones that we want to talk about today, where deep learning is deployed quite a bit. The CPU, it is the jack of all trades, master of none. Everyone has CPUs, everyone uses them. They have this very flexible instruction stream. You can branch, you can jump, you can loop, you can program whatever. Everything we use pretty much has some form of CPU in it these days that controls it at least. It handles this complex control flow. What's interesting about CPUs is obviously there's this control flow piece. There is this compute that's in there that's typically for scalars, although they do have some vector units, which we'll talk about shortly. But the memory system in CPUs is designed with this idea of low latency. So as you get closer to the compute, they kind of like the idea of registers. You've heard of register files where we store operands that we're going to operate on. Those are typically very fast. We talk about caches. The L1 cache or L0, which is closest to the CPU, those are typically really, really fast caches. You can quickly access the data that you want to use. As you move further away from the compute in a CPU system, it gets slower. It moves to a less efficient access, although it has its benefits. You can get more density, you can fit more of it. So if you go down to your DRAM in these types of systems, that's typically very slow and very costly. One thing about these CPUs is that you have this lower core count, you know, even though they are growing quite a bit, you know, you might hear things like 72 or 24 core count systems out there, you know, and maybe you've got some sort of dynamic processing where you can actually have threads in hardware. So maybe even though it's 24 count cores, you may be able to run, you know, 2 hardware threads on each core. So it looks like it's 48 different cores there because they're sharing some of the pipeline. And so you end up, but you still end up with a relatively low compared to some of the other options that are out there, number of threads or core counts of work that can be done in parallel. As I mentioned before, these things are so good for complex control flow. You know, they are doing techniques to deal with instruction level parallelism. They're saying, hey, these 2 instructions aren't dependent upon each other, so they can go out of order and then it'll put them back in order, and it does all these things. And the other thing that it typically has is some sort of, it is common for CPUs to have some sort of vector unit attached to it, a SIMD engine, as we call it, where you have a single instruction and you may have a vector of values that you're going to operate on. So to do the same operation on this vector of values, you know, these are the vector extensions, the Intel vector extensions that you see out there. And it is common for people to utilize these to speed up applications where SIMD operations will go well. You know, it's very viable for these for that type of application, and is commonly used. What's interesting is these CPUs are very useful, especially when we talk about limited parallelism. If you don't have a lot of work that can be done in parallel, or you have a lot of work that's completely disjointed, you can run like 16 threads, each one doing something different. CPUs might be very viable for that. Or if you have lower memory requirements. One of the things about using CPUs is, if you know, there's many times where, hey, everything in your application's on the CPU and you don't need a really big model to run. You don't have a high flop count, high memory footprint model. Maybe a CPU works well for there. And so you can just keep it all on the CPU because the rest of the application is there. The other thing to note is that even if we talk about this idea of CPUs and where we're running models or using them in DL, it is quite common that, or more than likely, that inside your system, a CPU is coordinating everything, or something like a CPU is coordinating it. There's usually some general purpose processor that's kind of in charge of keeping everything coordinated and running together. If you look to the right here, this image, this is just an example of, you know, the general hardware that exists on a CPU. You know, the L1 cache, you got compute and execute. I just wanted to give you guys an example of what that might look like, because next we're going to move on to the next level of hardware that we want to talk about today. And that will be the GPU. GPUs are basically originated as application-specific processors for graphics. Graphics involved a lot of matrix mathematics, and so GPUs came up being able to do that math well. lots of parallel compute, right? So it's a fully programmable system designed around that idea. And what's interesting about that, in order to feed that compute, keep it going and fed, unlike the CPU, which is designed, a memory system designed primarily for just low latency, the GPU memory system is actually designed for high bandwidth, high throughput. So it is designed to run a lot of threads in parallel. And in order to run that much compute in parallel, you need to keep it fed. You need to make sure you keep feeding that data as efficiently as you can. And so the GPU memory system has some capabilities that the CPU memory system typically doesn't. And I'll talk a little bit about this in the next slide when we start talking about things like a little bit about memory coalescing and things like that. Okay, which is the idea, just to give you some idea about memory coalescing, what'll happen is on the GPU, if multiple threads are requesting data and the data's close together inside the memory system, it will actually merge those requests so that it can limit the number of full memory requests it has to do. So it'll just request a big block of data and bring that back as part of the memory system. So memory coalescing is a big deal and really provides for a lot of efficiency on these systems. Now, one thing about GPUs is they are very efficient when running in lockstep. But unlike a SIMD engine, they don't have to run in lockstep. Divergent behavior, meaning basically all the threads that are connected together, if you look to the right, this idea of them operating in like a wave, you got these little green things sort of warps, things executing together. It may turn out that a warp can actually, hey, one set of threads in this warp goes down one path, another set goes in the other. The GPU can handle that and is designed to deal with that, but they work most efficiently when they're running all in lockstep. Okay. So, and as the way things operate is you kind of have this idea of this SM, simultaneous multiprocessor, which is basically a bunch of these are on the GPU running in parallel, each one accessing their L1, and the SM is trying to run as many waves as it can in parallel. And it just keeps operating them. And you kind of see to the right this idea that if we can keep the GPU 100% full, we're great, but sometimes you don't have enough work to deal with that. And so you kind of have to tile your work out, and that's where you start to get into inefficiencies. But what's great is, I was just showing this diagram, what a full GPU really looks like. If you look down here to the lower left, this is H100 in all its full glory. 144 simultaneous multiprocessors, each one with lots of individual CUDA cores. And it does support that idea of the memory request coalescing. So if the SM has lots of threads requesting data, it'll combine them all and get us an efficient fetch back from memory. The other thing about these GPUs is we have this ability, we have custom units. If you look here to the right, we have the idea of this tensor core that does a good job of just doing math operations. We have a we have the tensor memory accelerator. These are custom units that are designed to give us performance for these common cases, these common operations that are going to be there. And so we want to make sure that the codes that you work on when you launch a model, you're going to get the most out of these GPUs by making sure these are being used. And we'll talk a little bit later about what tools we have and that we provide that give you these accesses. The other interesting thing to keep in mind is the data types matter. The GPU supports multiple data types, especially for deep learning, int8, FP32, FP16, BF16, FP8. One of the things that we know a lot when you first get started for your deep learning models, you're probably going to start off in FP32. You're going to prove your network works. But then when you get to the nitty gritty of trying to get efficiency, you're going to want to go to the data format that is the smallest, because that gets you to maximally use your system. It means you're doing computation for the lowest cost and you're fetching the least amount of memory. And that's what you want to be able to do. Now, one of the reasons this is important is at the end of the day, we have these big compute systems, but what we're going to end up doing is we are actually mapping our work to this big compute system. So I just want to talk about a little bit about how the general idea of the problem happens on the GPU. There's only so much compute, for example, in an SM. There's only so much compute on the GPU. And a lot of these models have way more operators than we have ALUs, right? So what you end up doing is you end up taking the problem and breaking it up. You're going to hear this term, you'll probably hear it called tiling, is a common term for it, where you're going to tile the work. So you're going to split up any of the work you're doing into tiles and then split that work up within the GPU. And once again, memory changes as you get closer to the compute. So you get this higher bandwidth, but lower size memory as you get closer to the compute. So you can keep, like in the GPU especially, so you can keep these compute engines fed, but you still have to split the problem up to make sure you can fit in the different levels. And L1 is typically smaller than the L2 cache. And then you have DRAM, which is usually a large amount of space, but accessing DRAM is typically slow and costly. Okay. So when we talk about doing things on the GPU, we're really trying to get things tiled and placed into different levels of memory properly. And really, we're splitting the work among the SMs efficiently. The better the tiling, the more equal we can make the tiling, the more we can keep things in last step, the more efficient the GPU computation will be, or the application. Now, we talked a little bit about GPUs. There is another common architecture that's being used today, especially for DL hardware, and this is systolic arrays. This is basically an array of ALUs or processing elements where you have some sort of buffers coming into the array. If you look here to the right, you have a set of buffers feeding the PEs on the edge, and then the processing elements or PEs, what they end up doing is each one does a little bit of the computation and then passes along some information to the neighboring PE. It could be as simple as pass the data you got from the buffer to the next PE so it can do a piece of the computation, or it could be send a partial result to the PE so you can actually compute a computation piece by piece. Typically, these PEs will have a small amount of local storage just to keep things in memory and be efficient there. And they'll do a simple set of operations. It may be as simple as FMAs. It may be something even more complex. It may be some activation functions, but it's typically a simple things that they do. Their data flows through the array. So basically, each PE is computing a part and passing along partial results, or passing along data so someone else can do their partial results. And then at the end, you typically have to aggregate these results to get an answer. Another thing about systolic arrays is, similar to GPUs to some degree, you have to have a host who interacts with this and controls the PE array. Normally, there's some controller inside the hardware that says, hey, configure all these PEs, configure their communication pattern, and kick them, and then tell them to go. And also configure the buffers. This does have a limited flexibility in that the PEs typically can only communicate, for example, to the PE directly to the PE next to them. So they have a fixed communication pattern, or some limitations in the communication pattern, I should say. And they typically only have a limited number of operations they can do. One thing about using systolic arrays is you've got to have a problem that really maps well to this hardware shape. Turns out in general, just like the GPU architecture can do matrix math very well, the systolic array can also do some matrix math very well. And so you see this type of architecture in things like if you've, the TPU or the Iris architecture are all examples where you have this systolic array, which is also commonly used for DL hardware. Now, when we talked about that, how data flows through there, let's just do a little example here. What would happen is these first two buffers would feed their data into this first PE in the first cycle, just to show you how the data would flow. In the next cycle, they may pass along the data to the next PE, pass along data to the next PE. So the data continues down, the next buffer passes some information in, data passes, and you'll see now what we have is 1, 2, 3 PEs that would be working on it. The next time you'd actually have all of these PEs working, where these PEs, this PE and this PE are doing their first bit of computation for this work. This PE and this PE, also this PE is doing their first bit of work. This PE is working on their second bit of, these two PEs are working on their second bit of computation. And this PE is actually on its third bit of computation. And in general, that's how systolic arrays kind of get going. They flow the data through, they get going, and once they've gotten everything full and the computer's mapped well, you'll see them all working on a piece of the data. And once they're done, they will then send things down to like the accumulator to accumulate results and things like that. So one of the things that's interesting here is what we're saying here is, unlike, say, like the CPU or GPU, which really likes to use local register files or shared memory to store intermediate results, the systolic array really doesn't want to do that. It just wants to pass the data on to the next ALU instead. And so it's very different in how it handles things. And the last thing I want to talk about here is the idea of custom accelerators. For example, NVIDIA's NVDLA, Deep Learning Accelerator. These things are in general configurable, not programmable. Okay, this means you can tell them do specific things through configuration registers, through some sort of setup, and they will do those things. They will do them well. If something new comes out, an accelerator typically cannot adapt to that, okay? In our case, our NVDLA is targeted for inference. So if you really want high efficiency inference for your networks, then NVDLA, which is in our Jetson products in particular, Jetson Orin, this thing can really rip and give you very efficient inference on these networks. However, it doesn't come free. There are some things that, it targets specific data types. As I said, it's targeted for inference. And there are some restrictions on the sizes because it is still an accelerator, but it is very efficient. What's thing to keep in mind is when you're dealing with custom accelerators, especially for deploying inference and just deploying networks, and even just training for that matter, you need a very good software ecosystem. One of the difficult things about it is, someone has a network. At some point, you need to transform that network into something that the accelerator can use. You need to figure out what are the configurations? How do I use them efficiently? And how do I get my network down to something that'll work here? And that's where, for example, in the video, we have TensorRT, which is able to actually generate good configurations and data for the NVDLA system and go to use it. Okay. And we'll talk a little bit later about TensorRT, just a little bit, as something you should look at for definitely trying to get that maximum efficiency out of executing your system, executing your networks. And as I mentioned before, this is commonly used in edge inference in places, NVDLA at least. You will see typically these type of accelerators edge inference, although we are starting to see more accelerators show up in data centers and things like that. There's work coming out of various companies that they're working on their own accelerators and things like that. So, but as I mentioned, these are a lot less flexible. And so if something new comes along, well, you're just gonna have to deal with it. And now, one other thing I wanted to talk about, which has become very common and is out there quite a bit, and actually there are some examples of it in the Jetson Orin and Apple M2, is this idea of system on chips or SoCs. And what's interesting is these contain not one of those compute things I was telling you about, but usually a multitude of them. You usually have CPUs and GPUs and accelerators all on the same system, right? And so you kind of have the shared memory system. You have these things commonly trying to communicate with each other. So there's some sort of shared memory quite a bit. They have this way of managing the system and trying to optimize where things are running. And so this actually creates an interesting question and set of challenges, which is, what exact compute unit should my system be running on? Should it be running on the CPU? Should it be running on the GPU? Should it be running on an accelerator? How can I use all of them at the same time? How do I manage the energy and power and things like that? And this is where having a good software ecosystem really comes into play. Having something that understands the idea that you might be able to run it on DLA or you might be able to run it on the GPU, which one is maybe the best one, or if you're going to run it on that one, how do I get it the most efficient on that piece of hardware? And this is where you start to see things where people are running networks on things like, fully running it on, say, a MacBook Pro or something like that, because they're utilizing all the different compute elements to get the efficiency out they need to run these applications. So, and at this point, we've kind of talked about the different types of systems that these can run on, right? The SoC, which is actually an aggregate of all these different compute engines. We've got the CPU, the GPU, the accelerators, systolic arrays. There's one other thing that I definitely wanted to talk to you about today, or there's a few other things, but one in particular is all about the importance of memory accesses and how they play such a large role in making sure that you're efficient, okay? So if we think about just the general idea of what a accelerator or even just a compute engine looks like from a very 10,000 foot view, very abstract view here. We have DRAM, which has memory. We have some sort of on-chip buffers. Sometimes they have compute, especially in accelerators. Then this on-chip buffers or caches end up going to a register file, and then we have some sort of main compute that we work off of. Memory movement is so critical because of, we always like to look at the number of flops and how many flops something is taking, but here's why memory movement is super important. An 8-bit integer multiply takes about 0.2 picojoules. However, fetching 2 8-bit operands to do that multiply from DRAM takes 128 picojoules, right? That is almost 1,000 times more energy just to get the data you're going to operate on. Even if we start talking about, hey, we've got these on-chip buffers that we're going to use, fetching 2 operands is still 1 order of magnitude more expensive from even an SRAM than doing the multiply. And this is why it is so important as we start talking about optimizing this. What you want to be, one of the key things you want to be optimizing for, regardless of your hardware platform, is the data movement. Energy and efficiency are critical, and making sure you get as much reuse as you can out of the data. When you fetch something, leave it as close as you can to the compute to minimize that excess energy and reuse it as much as you can. And we're going to talk a little bit about how you can measure that and how to utilize that. Now, what's interesting there is I mentioned, oh, you want to get all this reuse. It turns out what we're talking about is this the idea of mapping. So let's look at convolutional neural networks, a convolutional layer, right? You have a bunch of weights, you have some input activations, you're generating some output activations. This is a simple 7-dimensional loop. Say simple, it's been around for a while. So you have this algorithmic way of dealing with it. What you want to figure out is, how do I tile it? How do I map this compute work and this data to the hardware system? How do I place it? So you want to get the most reuse. You want to get the convolutional reuse by using the same filter weights as much as you can. You want to get input activation reuse. If you've got multiple filters that are going to use the same input, you want to try to reuse that as much as you can. Output activation reuse, you want to basically be reusing the output activations across the channels. And you want batch reuse, right? Hey, if I can keep my weights and reapply the filters to some new inputs, fantastic. And you want to be able to reuse, you want your hardware. Your hardware has to be able to efficiently communicate, and you want to be able to map it to these PEs. And it turns out this is actually a pretty complex problem to figure this out, but it's a very important problem. Given a layer and hardware, there can be a ton of mappings, millions of mappings for a single workload, and just a ton of mappings even for a single layer. So this is an example where if we look at the picojoule Mac relative to energy multiplier, and look at all the different mappings, you actually get this idea of this kind of flow of, hey, it turns out that some of these are definitely more energy efficient than others, right? The spread is a 19x in energy efficiency. Only one mapping is optimal. 9 others are within 1%. And so we need to figure out how to map your workload, map your network to your system. Beyond just saying, oh, I'm doing this convolutional layer, there's a question of how you execute that convolutional layer, how you execute that network. That becomes important. And so this is just me. I wanted to plug a little bit of work that's come out of NVIDIA research, working with MIT. This came out of our group, an architecture research group, where we actually have a tool called Time Loop. And it actually tries to take the architectural specification and do a search to find these mappings to get you this energy, along with Accelergy, which is used to estimate the energy. And the reason I'm bringing this up is not just to plug the work, but also to say, yeah, these are the types of things that become important as we're trying to optimize the compute, as we're trying to optimize for getting the most efficient full stack capability. If you want your network to run the best, you may start looking at this and saying, oh, well, how are we tiling it? Especially if you go full low level into doing this. Now, I talked a little bit about the mapper and things like that, mainly because I want to now go into the core concepts from, in my opinion, those of us in the architecture world, the hardware world, the core concepts and metrics that we use to try to get an idea of how well these systems are executing. Okay. And one of the key concepts here is the idea of latency. And this is really the time to complete an operation. The latency is really how long did it take for something to return the answer or request I told it to do. That is the latency. Units is typically time. How long before it's complete. Examples might be, you may do an add. Maybe your hardware can do an add one. We'll actually do an add operation and have an answer in 1 cycle. Maybe a divide operation takes 10 cycles. Maybe a function call takes 10 nanoseconds to return. That's the latency before it comes back. Now, this needs to be compared to throughput, and that's the rate at which work can be completed. So basically, how much work gets done over a unit of time. So this is different. This is something that we commonly see networks measured at for performance. People will say frames per second. You know, you'll say, oh, this memory system can do bytes per second. So this is really measuring how much work. And there's a difference between these two, which we'll cover in the next couple of slides, just to make sure to hit home the importance that they are not the same thing. Throughput is not necessarily 1 over latency. Okay, a lot of times people will look at it and they'll say, oh, or latency is not 1 over the throughput. They are not necessarily related in that way, and it depends on your system. Other key factors are energy per operation. You know, you saw me mention how much energy it takes to read the various values or how much energy you do a math op. This is important to understand that the average energy to compute an operation is a key metric to utilize, along with how many operations you're doing and the different types. And that's why you have things like quantization, where you try to get down to 8 bits, because it's a lot less energy doing an 8-bit math op than a 16-bit math op. And then you have power, common thing, but this is the energy over time. And then you have this idea of perf per watt, which is basically saying, how many operations am I doing per second? And how much energy does it take for me to do it? It is literally a measurement that says, for example, flops per watt is a great example where you say, hey, I care about efficiency. I may be able to get to 1 teraop, but how much power does it take for me to get to 1 teraop? And that's where this comes in. But moving to the next piece, which is latency versus throughput, just a simple example. And I'm curious, so I'm going to open it up for if anyone, I want you guys to think about this really quick. You know, if I tell you the system delivers a throughput of 30 frames per second, out of these choices, what's the latency of this system? Is it 33 milliseconds, 66 milliseconds, 1,000 milliseconds, or 2,000 milliseconds? Everyone still there? Can you hear me? Sorry, my headphones kind of died on me there for a second.
We are here, Jason, waiting for your answer, actually.
Oh, okay. All right, so the actual answer to this is yes. All of them could be right. It turns out, literally, I can deliver 30 frames per second on average with any of these answers. And it deals with the fact that throughput by itself is not usually enough to actually specify your system. Turns out, if I do 1 frame per execution, yep, 33 milliseconds. But what if I do 2 frames? Then I can take 66 milliseconds. I could do 1 second to do all the computation and only return you something every 1 second. But when that 1 second, I return you 30 frames. Or I could actually return you 60 frames every 2 seconds. Turns out, guess what? If you take the amount of time over the number of frames I'm returning, that's 30 FPS. And so one of the things to keep in mind when you're trying to figure out what you actually need your hardware to do or how you're going to specify it or what you're trying to do is to pick the right target and understand that throughput by itself may not be enough. If you're in a low latency situation where you need to, you're getting a frame every 33 milliseconds. If you're getting a frame every 33 milliseconds and you're going to get another frame in 30 milliseconds and you've got to return an answer, guess what? Then it matters about what the latency is versus what the throughput is. Okay. And so if you look down here at the bottom, turns out, you know, yeah, exactly as I was showing above, hey, A and B, these 2 different lines, they both are giving you 30 frames per second. And so this is just coming from the hardware guy to some degree that, yeah, it's kind of interesting. I see a lot of work that says, hey, our stuff's able to run at this many frames per second, but the batch size will be 32 or 64. And it's like, well, if someone's trying to figure out how long of whether they can use this in their system, we really need to have some idea of what the latency is between returning executions. Now, beyond the throughput versus latency, there's some other things that are pretty useful for understanding the performance of what's going on in your DL hardware. One is the compute bandwidth. This is basically how many math ops you can do over time. You know, if you've got 1,024 compute units, you got a 1 gigahertz clock, you do 1 operation per clock, you can all figure this out. That's basically 1 teraop, right? If you do 2, well, that's 512 gigops, right? And then there's this next question, which is how well are you using your hardware? How well are you keeping your compute fed? Or how well are you using your compute in a certain sense? So it's a fraction of the peak compute bandwidth achieved. So for example, if your hardware could do 1 teraflops, but you're only using 400 gigaflops, then yeah, you're at 40%, right? Compute bandwidth utilization. What that means is you could be pushing your system better if you can get more compute running on that hardware. Their hardware is ripe for more compute to be utilized. Now, on the other end of this is for every bit of compute, you need to feed it data, right? So that's where memory bandwidth comes in. This is the rate at which you can fetch data out of the system. And this is just, bytes per unit time, usually in some sort of gigabytes or megabytes per second, right? And high performing hardware has very high numbers there. What's interesting is the memory bandwidth utilization is similar to the compute bandwidth utilization. So now we're looking at what is the peak bandwidth your system could achieve and how much of it are you actually using. Turns out if you're using only a fraction of your memory bandwidth and only a fraction of your compute bandwidth, hey, maybe you should try to fetch more data. Or if you're using only a fraction of your memory bandwidth and you want to get more compute, figure out ways to be more efficient on that. We'll talk a little bit more about what these mean and how we can use these to improve the capability of the system. And another thing I want to talk about is this idea of arithmetic intensity. And I don't know how much you guys have heard about this, but if you go back to what I mentioned before about the cost of fetching data and being able to reuse data, arithmetic intensity is all about how many operations, flops, do you do per byte of data fetched. It basically says, how often are you reusing this data that you fetch? The more you reuse the data, because as we mentioned before, math ops, doing math is a lot less energy than fetching data. So if you can reuse data and not have to refetch it from the next level, congratulations, you are saving a lot of energy. And high arithmetic intensity really does lead to efficient hardware usage. And that's where you get to an efficient application. Just some examples about estimating the performance of your system. So let's say you got some idea, you want to know, well, how good do I think this particular network could be on the hardware that I have? One, the simple thing is obviously compute the flops and the layers, right? We all have looked at it. We know what Conf2D looks like. We have for years. We can compute the math, right? We can also compute, what the bandwidth is for that thing, because you can actually do the math here and say, well, here's my input tensor, my output tensor, my parameters. If for some reason I had to fetch them all, I can figure out how much bandwidth it would take to move that around. And now I can actually have an estimate now of how many flops do I need and how much bandwidth does it take. And so you can actually take your system and say, well, in the ideal world, most manufacturers, we will put on there, this system has this many tera ops peak or whatever. You can use that to figure out where you're at relative to what your system could do. Right? Realistically, though, I will note, in some cases on some systems, you got to do some sort of derating. You getting 100% of your compute bandwidth would be very, very impressive, is what I'm going to say in many cases. But one thing, taking this idea of we have these memory, we have this compute bandwidth, this memory bandwidth, let's talk about how they affect performance on the hardware, or at least what you should care about, how you can categorize them. We typically categorize things on the GPU as either math limited or memory limited, okay? And what this basically means is you're math limited if you're using a high amount of the compute units, while the memory bandwidth is not too high. So think of it as, hey, I am only using, say, 30% of my memory bandwidth, but I've got 50% of my compute units being used. Right? All right, let me say that again. Let's say I have, I'm using 100% of my compute units, but I only have about 30% of my memory bandwidth. Sorry. That's what I meant to say. And what that basically means is that, hey, it turns out that this ratio of memory bandwidth, of the bandwidth over the peak, I'm basically saying that, hey, I am math limited because I'm using all the compute units. And so even if I had more memory bandwidth, it will not improve the performance. I don't have any more compute on this platform to give it. Memory limited, on the other hand, is kind of the opposite. It basically says, hey, if I've got my memory bandwidth system pegged to the max the system can provide, but the compute units are only like 30%, that basically means, hey, I just can't fetch enough memory to keep the compute units fed. And one of the great things is you can use things like the arithmetic intensity to kind of give you an estimate about where you're at, right? In general, if your peak bandwidth and bandwidth if your peak compute bandwidth over your peak memory bandwidth is actually less than the ops per byte you're getting, you're probably math. And so this table here, which will be brought up later, you can actually get an idea of the arithmetic intensity, kind of give you some ideas of what's going on in these different systems. You know, a linear layer, a ReLU layer, you know, these are all memory limited, which means, hey, with more bandwidth, we could do better. Or if we can use our bandwidth better, we could do better. And so just a note, these are the 4 quadrants you kind of end up with this idea of compute bandwidth and memory bandwidth. If you're in the upper right, you have high memory bandwidth utilization and high compute bandwidth utilization. Congratulations, you are utilizing your platform to its fullest. You have written some code that is awesome, and be proud. Go get yourself a coffee and tell your boss how great you are. Now, if you're in the upper left-hand corner where you have low memory bandwidth, but high compute bandwidth, you are compute limited. Basically, is there something you can do to get more compute out of the platform? Could you possibly go from 32-bit to 16-bit numbers? And a lot of platforms like GPUs have this ability where, hey, it turns out that our throughput at a lower precision is actually faster. Or is it not faster, but you have more compute. So you may be able to say, hey, I could do 500 gigaops per second at FP32, but now maybe I can do 1 terahops. Okay, so things like that. On the other hand, going down to the other quadrant in the lower right-hand corner here, you're memory limited. At this point, basically what's going on is you have high memory bandwidth, but you have low compute. So you want to look at things you can do there. And then finally, if you're in this bottom left-hand corner, you need to look at the algorithm and the code and the compute platform altogether. Maybe this is not the right compute platform. Maybe this code doesn't match it, or maybe your code just has issues that really need to be worked on. So just a little bit of some hints on dealing with some of these issues. To give you some idea, you notice I mentioned about changing the different data types. You can actually see here on the right how the amount of compute throughput you get changes as you choose your data types. And even as you move to new hardware, like on the GPU, obviously, using the regular SM number of teraflops as opposed to the Tensor Core, which has far more teraflops. So if your compute bandwidth limited, move to a different numerical format. See if you can run at 8-bit, try to run at 8-bit, right? Because as we see here, you get more teraflops out of that. Rework the algorithm to try to use less compute. Is there some new way to do it? Maybe some parallelism changes. Maybe you can find ways to group things better. Maybe there's an alternative that uses less compute. Use structured sparsity, which is something we have in our GPUs, which is the ability to basically say, hey, I got some 2 to 4 sparsity. So what's going on is in essence, the number of flops the GPU can do, it goes, and your algorithm goes up because basically you're only telling it you're basically telling it, I'm going to get rid of half the flops. You know, structured sparsity basically says, hey, if my matrix is 4 by 4, I'm only going to do math for a 2 by 2, but it's done in a way that is efficient. And as I mentioned before, use specialized hardware. All of these will help you squeeze more compute out of your system. Memory bandwidth limited. Hey, move to a different numerical format. Yeah, that's going to come up a lot. Turns out, going from 16-bit to 8-bit means you have to actually fetch, even if you fetch the same number of operands, you're fetching less number of bytes total. Try overlapping memory transfers. See if there are ways you can stage data. Restructure your data to make the transfers better, or resize the problem. And if you're both of these, you really need to look at your problem and refactor your code. And one thing I want to remind everybody here, and this is just a piece here, is sometimes when you're using libraries and things like that, they are written very generally. And sometimes it's worth writing your own custom CUDA kernel and using that CUDA kernel to get the most efficiency you can. Now, one thing I mentioned before was TensorRT. And this is an NVIDIA tool that basically allows you to take your network and optimize it for running on GPUs or even our DLA engine, okay? And it does a few different optimizations And that really allows you to take advantage of it. So if you're trying to optimize, especially for inference, if you're trying to optimize for inference, TensorRT is something to definitely look at. It does these things that are commonly used. Like, for example, it will try to quantize your model to 8-bit and preserve the accuracy. It'll try to do some layer fusion and tensor fusion. We'll talk about that next, what these are specifically. It can try kernel auto-tuning, trying to select some of the best data layers. So kind of like it can help with neuroarchitecture search. It can dynamically allocate and deallocate memory. It can support this multi-stream execution, so you can do more things in parallel and doing time fusion. So if we just, to kind of hammer home this a little bit more, it can convert this model to 8-bit without requiring new training. Obviously, quantized-aware training probably would get you even more accuracy back, potentially more useful in all situations. And maybe your situation you will lose some accuracy possibly, but it does its best to get you down there without losing accuracy. And if you do lose some accuracy, some quantization-aware training can help with that. Layer fusion. This is the idea of merging different layers or operations together so that you don't pay the cost of, for example, doing ReLU by having to refetch the data back from memory after you just did a convolution with it. Turns out, ReLU itself from a hardware perspective is fairly simple. Check the sign bit, right? If the sign bit happens to be set, then that means make this thing 0. Otherwise, just pass the data through. Well, that can probably be tacked on to the end of your convolution calculations. Why should you have to go refetch some data just to do that simple operation? And there's a few other operations you can put together. So it decreases these round trips to memory, saving you energy. The kernel auto-tuning, more efficient ways to perform a layer. One of the things here is, if you use cuDNN, if you ever look at what it's doing sometimes it'll take a convolution layer and turn it into a Winograd transform on it. Turns out, depending on the size of your kernel, a Winograd transform is a more efficient way to do convolution. As I said, the memory, it's going to release that memory so you take up less space. You can share the data a little bit better with streams, and you can optimize. The time fusion is from, when we're dynamically doing time steps on like RNNs. So, as I mentioned before, it does a lot of optimization. It takes network generous, highly optimized version. I think one of the things to keep in mind, if you want to use the DLA, I do recommend using TensorRT. It will generate that model. It will do the best to generate that model. And it even has a fallback thing where it'll say, oh, I'm sorry, I can't run it on the DLA for whatever reason. So I'll run it on the GPU. It's very useful. So definitely see what you can do there if you're trying to use the DLA engine. And it does have a special engine for optimized network execution. And just a note here, TensorFlow has integrations for it. PyTorch has integrations for it. We even offer Docker images that are ready to go with TensorRT. And now we're to the last little bit that I want to talk about here today. And this is the profiling tools we have for figuring out what's going on with your application. And the two major ones I want to talk about are Insight Systems and Insight Compute. Insight Systems is all about getting idea of system level timing performance. Things like Insight Compute is all about getting things like individual kernel performance and understanding like flops and occupancy. So as I mentioned, Insight System, you're trying to get information about the execution. This is an actual screen grab of a timeline from the GUI. So you can actually you can generate a report and tell Insight Systems, hey, show me what's going on. You can actually see, hey, these are the kernels. This is what time this is doing. This is executing. And if you hover over things, you can figure out things like, oh, well, what type of launch was this? How big was the grid? How much local memory did it use? How much shared memory did I use? What was my latency of doing this? This is all very useful information to get an idea of how well you're using the hardware. And it's a nice GUI format if you want to use that. Now, being who I am, I lurk in command line. So I decided just to show you guys, there is a command line form of this where you can do this to generate a report that can be post-processed on the GUI. So I'm literally showing you this command so that when the slides are available, you can come here and say, oh, this command is how I would use Insight Systems to profile from the command line. Okay. And in this case, I'm telling it, oh, these are the APIs I care about. CUDA, cuDNN, cuBLAS, which are all common libraries in execution of DL. And then different ways to capture the data. So, and what's interesting is after you've done that capture, you can, from the command line format, you can actually run this idea of running a stats and do a report out. And down here, you can actually see an example of that report out where it'll actually tell me, oh, 22% of my time was spent on this particular kernel. So you can actually figure out what kernels are you using? Are there more efficient versions? Which ones are being used by the software stack? And then you can take a look and say, hey, should I be looking at optimizing whoever's calling that kernel? And there's another capability, which is this idea of inserting regions that you care about into the profiling. And you can actually see it here, where you can actually name regions and it'll give you information about what's going on in the system in that and put it back onto the timeline. So you can actually see what GPU kernels are being executed during those regions and get an idea of where you should be spending your time. And then there's Insight Compute. This is the one where it's a high overhead. Just to be clear, Insight systems, relatively low overhead, great. Insight Compute, high overhead, but very detailed. In this one, you can find out things like how many times was a 32-bit Mac operation done, or exactly how many bytes of data were fetched from DRAM. And so in this particular case, in this particular case, what I'm showing down here, just to show you, this tells me how many bytes of DRAM were fetched for this particular kernel name here. Now, the other thing you can do here, which is great, is you can do this one command right here, this NCU set full report net. That will actually give you a report out where it'll tell you what kernels it ran into that it thinks are compute limited versus memory limited, and will give you tips on how it thinks you should optimize. And you can also get other metrics, like I said, the DRAM bytes and things like that. And you can always query what metrics are available from your system. And finally, well, not quite finally, but close to finally, the final tool I'll talk about, at least, is these NVTX regions, this annotation tool. This is where you basically insert regions that you care about, and then our profilers will use those names and give you aggregate information about what's going on in those regions. So there's Python packages available to insert them. So if you're using like PyTorch, like I do a lot, I can go in and insert and figure out exactly what's going on in these regions, and it can generate reports and help you pinpoint where exactly you need to be paying the most attention for efficiency. And this brings us to the idea of profiling tips. Some things to keep in mind. One, query your supported clocks on your GPU, and if you're doing profiling, lock the clocks. And what I mean is our GPUs by default will vary the clock based on temperature and things like that to keep the GPUs cool and to keep things efficient. The problem is from run to run, you can get very varied times in terms of your execution times. So running NVIDIA SMI and locking the clocks actually gives you a fixed GPU clock, and I meant to put max right there, that you want it to be at, because now you can go run to run and measure whether or not your changes are actually affecting it, or if it was the fact that someone else was using that same system and they heated up the system enough that it tried to drop the clocks to deal with that temperature change. And also be a good neighbor, always release your clocks when you're done. Some other system considerations to think about: always stop your non-essential tasks. There's this idea that you want to do some warm-ups. So you may want to run a few iterations of inference or of training before you start doing the profiling. And you may want to profile only the regions of interest. So using CUDA profile start and stop, the NVIDIA INSYS and Insight Compute NCU, you can set them up to only activate when those are called. Trust me, when you got something that takes 10x or more execution time, that is very valuable. And then make sure you do your proper synchronization when you're done. One of the things that people fall victim to is they don't properly synchronize, and they're like, oh, why is it so short? All right, this ends my section about hardware. Others will go into it, but this is from the hardware perspective. These are the things we normally look at when trying to do this performance.
Thank you, Jason.
So, all right. Thank you, Jose. Are there any questions, or are we moving right on?
So any quick question? Sure, there's a mic there.
Thanks for the talk. So these days we have a lot of tasks where like we have graphics like workloads within deep learning. So what is the strategy on when to write custom CUDA kernels versus write like custom shaders for running these sort of, say, for example, ray marching like operations?
generally what I will do is, so this is from my own experience, right? I typically will go in and say, hey, what libraries is it doing for these calls? Like your question, if I'm understanding, is should you be writing CUDA versus shaders? Is that the core question?
Yeah.
Okay. My general rule of thumb is, just to be clear, I have not done a ton of apps with that type of combination, but my general rule of thumb is if I am doing something that is definitely more like a DL compute type of thing that is, there's some graphics portion to it, but it's primarily going to be compute based, it would be to try to do the CUDA kernel first. The reason is that, we have a lot more libraries in CUDA. You can do some custom shader kernels, but I think for some of this DL stuff to get the optimal efficiency, it's a little bit more challenging to get access to those libraries when doing the graphics side, right? So,
yeah.
But at the end of the day, you do what's best, because I know you can mix some graphics and CUDA stuff. So,
yeah. Cool. Thank you.
One quick question.
Thanks
question.
So much for the great talk, Jason. Since you have a very nice hardware perspective, I'm a TensorFlow, PyTorch kind of user, higher level. One question I have is, what happens when you have bigger batch sizes? Because your weights are static, but then you've got activations going through. So does it sort of make more copies of your static weights inside the SMs, or is that not affected by the batch size?
That question, part of that question depends on what you're using for your stack. I know you said you use PyTorch, but what you have enabled back there. What I would generally say is this. When you have more, remember I mentioned tiling before, right? It will actually tile with it'll basically think of split. If there's too big of a batch size to sit on the GPU, what it will basically do is do one part of the batch. In general, this is a general way to handle that. It'll do one part of the batch the first time and then do another set of the batch another time, right? Literally just tiling it by splitting the batch up, just to run it through there.
Thank you.
Thank you, Jason. Let's thank Jason again, please.
All right, thank you guys. And
so after the hardware perspective, now Pablo is going to talk about how can we, from a software perspective, maximize the use of the GPUs. Pablo is a principal scientist at NVIDIA. He is focusing on inference, efficiency, deep learning, and he has worked on model acceleration, model inversion, and in the end, model definition, and everything that has to do with better performing networks. Please welcome Pablo.
Yeah, common problem, right? How to share. Not clear, do you know? Yeah, but I'm sharing on screen.
Share just yours.
Okay, this will work. Right, cool. Hello, everybody. Thank you for coming. We had an amazing presentation from Jason on the hardware perspective. Now we're going to look into software. And just like a disclaimer here, any results I'm going to present, it's more from research perspective because we are at the research conference. And I'm particularly myself is also a research scientist. And at some point I was asking these questions myself, like, okay, how can I get best out of the GPU hardware? Because we train obviously a lot of neural networks. But if you have any particular questions, like why your GPU doesn't work as fast as you expect, then please contact our product managers. They will help on that front. And so in this presentation, we're going to have a lot of numbers, a lot of tables. I was thinking how to make it a bit more fun and found this picture basically that tries to summarize the presentation. So the problem we have here is how fast can we fry sweet toasts on both sides. If I have a single pan and I know that I can fry, let's say, like only 2 of them, on the pen. And like the most obvious solution is to do it in 4 minutes, and that's obviously not optimal because in kind of last 2 iterations, I can put only 1 toast. And so if you think it for a while, we can put this correspondence that my pen is basically a GPU that I have and I utilize. And my toasts are basically data or neural network like data in it, because in many cases they're interchangeable. So apparently I can do this more efficiently if I use a SmartL algorithm. And I think that's like my entire presentation today is going to be about that, like how basically without changing hardware or my data, how can I make things more efficient? And this is how agenda gonna look like. I will start with really basics background like gems. We will see how they're implemented. Then we will try to understand the DNN performance on why things compute in particular way. We will see this first set of recommendations on how to make networks faster if I work, let's say, with CNNs, how I can maximize tensor cores. And then we're also gonna cover like various topics that help us with training networks or running them more efficiently. So that's a quick overview of GPU architecture. It's something what Jason was talking about. So we'll be quick here. We have basically streaming multiprocessors that do most of the jobs that we send to compute. It has access to L1 cache that's super fast. And then all SMs can access L2 that's slower. And then if I need to go completely off the chip to DRAM, it's going to be slower. So obviously, closer I can put my data to SM, faster things going to be. And there is a particular example for A100. So we start with very basics with what's called general matrix multiplication or GEM. Basically, if we talk about performance, this word you will hear a lot. And this is because we can represent almost any operation in neural network through this matrix multiplication. And we can define it as this simple equation like C is equal to alpha times AB plus BC. So different frameworks implement it differently, but for PyTorch, for example, A is my weight, B is my data, and C is something like a previous memory allocation of the tensor. It can be like a skip connection or something. So now there is a quick example here with basically dimensions. If we assume A is M times K, B is K times N. Let me better use a pointer. Yeah, so then C is going to be M times N. And a quick example that the dot product here will result in M times N times K fused multiply adds. Or if I want to do this in flops, I will need to multiply by 2, right? Because multiply and add 2 separate kind of operations there. And so if my basically K is large, then I can ignore alpha and beta. And to understand performance on how fast this gem is kind of going to be executed on NVIDIA hardware, I need to revisit this arithmetic intensity equation, which kind of pretty simple, but it gives us in the end this understanding that it will depend on the flops and of course on the amount of data requires to access or to transfer. And this is a very quick example for V100, so which we know the flops to byte ratio. And now, so if I have a tensor of particular size with a batch size 128, you see my basically flops per byte going to be lower than what GPU can do. So I'm basically memory bounded by just transferring this data. But if I increase my batch size, I will have much more data to compute. And so this becomes mass bounded. And this is what we want from GPU is like for GPU to heat up, it just needs to do more and more compute. Now, this is a quick example of specifications for different GPUs on fused multiply add, on how many of them we can do. Since NVIDIA introduced tensor cores, things become much faster for these gems. And of course, it depends on your data type. We're gonna quickly talk about it. And there is a quick example how we can compute what my like flops throughput kind of gonna be. So I take this number from the table, I multiply it by number of streaming multiprocessors, and then I multiply by my clock rate. And so this is how I'm gonna get like kind of my throughput for different data formats. Now, the way GEM is implemented, it's actually quite important to understand. I have this matrix multiplication, and the beauty of GPUs is that we can parallelize it, send two different SMs, they're gonna do their compute, and we're gonna push it back to matrix C. And we can control this, or like not we, but software can control it by splitting this matrix into tiles, and then every SM gonna do this tile computation. And that's actually matters a lot on how the size of the tile I'm gonna choose. As Jason talked before, and I'm gonna repeat about tile and wave quantization will matter based on the tile size we're gonna choose. So obviously, if my tile size is very large, fewer SMs gonna be able to run it. I mean, of course, it's a ratio with respect to the matrix, but if it's too small, then I will have so many times to do this compute. That's also not optimal. And yeah, I mentioned optimal, so it's always interesting to see kind of optimality, what's going on there. For this particular example, we vary one of the dimensions k of my matrix multiplication with m and n being fixed. And so obviously you see that my kind of duration or latency to compute, it doesn't have like a constant cost, but for a particular numbers that's divisible by 8, we can significantly reduce the duration. And this was on a previous cuBLAST implementation. Of course, NVIDIA always improve these things. And so in a new version, things get more even, but still, if you have this knowledge, that your number, let's say, of channels divisible by 8, you're gonna get more of your GPU. And on the right, we see dependence on the tile size. So obviously, the bigger tiles, the better, as long as it can fit into SM. We will always get more flops throughput there. Now we come to the first thing that really matters is tile quantization. So when I split my matrix into tiles, size really matters there of the initial matrix. So if for example, my matrix is 257 times 256, then one of the dimensions I will have to have basically another, to launch another compute there just for this one basically column. So this means we need to carefully choose our matrix size, right? So that it fits into SMs, and yeah, moreover that we maximize the number of SMs we have on GPU. And so image on the right kind of shows that if I'm gonna vary one of these dimensions, I'm gonna see the stair-like pattern where my kind of number of, my kind of duration increases significantly if I just add, let's say, one more channel. And we will see this in my INS presentation on how we can use this to prune neural networks better. Another thing is the wave quantization. So once this every SM has job, of course, I don't have a limited number of them. So depending on this number of threads, I will run all of them up here. But then if I still have job to do, I will have to create another wave. And now what happens is that if this wave will not fit all of the SMs, it means some of them will just stay idle. And again, basically in this NVSMM, we're gonna see that our utilization is not 100%. So again, it means when we design networks, we should think of these sizes. And there is a particular example for A100 with 108 SMs, so that for particular tile size, ideally I wanna have 108 tiles total to execute all of them simultaneously and don't have these tails that are much less efficient. Cool, the background is done. Next one is understanding performance of deep neural networks. So this slide is actually the same as what Jason was showing. To basically understand the performance, there are 3 factors. There is memory bandwidth, mass bandwidth, and latency. And so my operations can be either memory limited or mass limited. Again, if I want to utilize GPU, I will better have my all operations to be mass limited. And so here is an example for different operations. And for example, the main difference between first and second one, I just changed the batch size, and my operation can go from mass limited to memory limited, which is not good. And for some other operations, I have a summary on the next slide. So we can roughly divide operations in deep neural networks to 3 categories. The first category is element-wise operation. It's, for example, is addition of 2 tensors. So I do operation on every element, and this is independent on other elements. And this is most of activation functions. Most of these operations tend to be memory limited, so we should minimize usage of them. Next set of operations is reduction operations. It's, for example, like pooling, or it can be batch normalization, layer normalization. And one thing about it is that I have to schedule kind of my job on GPU such that it stops and waits for all of the kind of elements required for this operation to be executed. Versus if I don't have reduction operations, I can, for example, start computing next layer while there are still SMs working on the previous layer. And so these operations, again, memory limited. Besides this, put in a compute barrier. And so we should minimize usage of them. Final one is a dot product operation. It's like linear layer, matrix times matrix multiplication. They tend to be mass limited. So we should maximize their usage. And one cool example we took from the paper on transformers. There is stuff on top. Let's close it. Can I close it? Yeah. Okay. So this particular example for transformer, they're super popular right now, and we can divide operations there into tensor contractions, statistical normalizations, and element-wise operations. And it's pretty interesting that if I just compute flops of these operations, we're going to see that most flops are on tensor contraction, right? Versus if I really going to check my runtime, the picture is going to be completely different because, again, I need to have this compute barrier. I need to transfer my data. So that's why in efficient community, we usually don't trust just flops, but we look into like throughput or exactly what is going on, considering the cost of data movement. Let's go next. Yeah, so a quick guide on how to find what's the problem in our current, let's say, execution of the network. We should look up the number of SMs on GPU, and again, imagine how ratio flops to bytes look, and if I can utilize all of the SMs. Then I should compute arithmetic intensity of my algorithm, and again, understand is it mass limited or bandwidth limited. If things are not going well, then we should check, okay, if my latency is barrier, it means I'm not having sufficient parallelization. So like, I'm not using efficiently gems, for example. I need to redesign my algorithm. We can see that I'm mass limited. If my arithmetic intensity is higher, and then finally the memory limited factor we also have talked about. So next is considering some recommendations for different networks. And so what we have here, I have probably told it so many times, but let's repeat it again. We would like our operations to be mass limited to fully utilize GPU. Ideally, we want to use tensor cores. And so to use efficiently tensor cores, I should think about the data format in which my compute is happening. I should also carefully choose the size of parameters in neural network to utilize them better. And now we're going to look into some of them now. So this is roughly what we can get for hierarchical models, like, for example, CNNs, where my resolution decreases while I'm going deeper into the network. So it happens that first layers in the network are usually memory limited. And so for these layers, we don't want to use something like depth-wise convolutions. We want to use full dense convolutions because amount of time I spend to transfer in memory is just so high that I can spend a lot of compute there and it will be not will not increase the latency there. We want to minimize the pooling. One of the simplest examples is like squeeze and excitation layer, where we need to pull over the channel. We don't want to have them here. We want to avoid layer normalization because even in inference, it's going to require computing the full tensor first. And yeah, so ideally we want to use something there that we can fuse later on, like batch norm and ReLU. And it also happens that last layers in network are usually mass limited. So we are fine there, like using depth-wise convolutions because they will reduce amount of arithmetics I'm doing there. Squeeze and excitations are fine. Layer normalization is fine. One also trick we can do is that if my input resolution is very high, so my number of channels is small in the first layers, as we saw previously, it's not optimal. So I can use some tricks like, for example, pixel shuffling to move my spatial dimension into channel dimension. All right, the next one is maximizing tensor core usage. So it also boils down to the shape of the parameters I use and also to the data format I use. So this is like just a rough recommendation for conv and linear layers, number of channels should be divisible by 16. For int 8, it should be 32 to fully utilize my SM. The mini batch size should be divisible by 8. Of course, usually the higher number is better, and usually for like A100, these numbers should be 128, 256, but this is just guidance for all possible GPUs. It even matters for sequence problems because it gets transformed into batch dimension, and there is also a recommendation of divisible by 16 or 32. We can also do some tricks to maximize the usage. Like you may all know that the best implementation for transformers, we stack QKV together, we do compute the matrix multiplications there, and then we split it back to key values and queries. And so, yeah, just a small thing you might notice that, for example, efficient net v1, mobile nets, they are super efficient and CPU, but when it comes to GPUs, they are not. And so that's why, for example, efficient net v2 was invented because it was just not following this guideline. Efficient net v1 was not following the things we just talked about. Another advice for convolutions. So for convolution, it matters in which layout we're gonna do our compute. So it can be channel first as the one by default, let's say in PyTorch, or it can be channel last, that's more efficient. And I think TensorFlow uses channel last, I'm not sure. So channel last is more useful as it's shown on this kind of figure on the left. So the channel last is gonna be the line on top. So it means more efficient. And if you want to do these things in PyTorch, it's also just 2 lines of code, and at least inference for sure going to be faster. With training, it's a bit more challenging to get speed up there. Another very important thing is how do we choose a number of channels? And this is pretty funny. So this is for first layer in neural network, when usually my resolution is high, like 256 times 256. And what happens that for first layer, for example, my number of input channels is small, like 3. So this is suboptimal, so the 3 is going to be this point. And it's pretty funny that by just concatenating one more channel that is just zeros, my duration will be decreased by a little. And this is also something that came up with NVIDIA software, because in the beginning, even channel 3 was also somewhere up there, somewhere higher. So this is like a simple trick, making sure my things are divisible, in this case by 4, gonna improve the performance of the neural network. Now linear layers and what we can do here. Again, these boring numbers, but always look to check by how much things should be divisible. at different data formats to run efficiently on Tensor Core. Particular recommendation for A100. Another recommendation that when we have a small number of parameters, then the number of input and output channels should be divisible by large number, like 64 to 56. And yeah, overall, like usually the batch size, we also want to increase as much as possible, as there was a question after the previous talk, because it's the simplest way to increase parallelization of compute that's going on there. Now for transformers, like transformers, of course, use a lot of linear layers, but particularly one of the kind of innovations or differences there is that we have an embedding dimension when we try to encode our tokens. And what's going on there is that I can simply concatenate like or increase my vocabulary size to be divisible by 8, and things gonna get more efficient. I think even Andrei Karpaty tweeted about it some time ago. So we have blue bars for non-divisible by 8, and then the green one I just added, let's say, four more elements there, and you can obviously see that my throughput gets increased. And this is for previous cuBLAS, for newer cuBLAS, the things the change is smaller, but it's still like definitely better to use a divisible by 8 by just concatenating 4 more, right? I increased redundancy, but my throughput increased. Okay, next stuff is about mixed precision and sparsity. So for mixed precision, we can look at this example of histogram of activations, particularly for network detection network SSD. And it's shown in logarithmic scale on X. So if I, like, let's say, use the entire range, that's going to be FP32. But what if I want to use a smaller data representation, like FP16? Then just looking at the, like, you know, the range, I might be kind of missing a lot. And so the very simple trick we can do here is introduce scalar that's going to shift the entire histogram. So I simply multiply my, let's say, activations by some number, and I can treat it on where it will fall in the FP16 representation. And so to find this optimal scalar, we actually don't need to do any compute. We have this AMP library that's part of actually PyTorch right now by default, and should be of TensorFlow, that will do this computation of the scalar by default. It's like it starts with one scalar, and it sees how much your like loss varies and adjusts it. And a small like note here on data types. Actually, when we do autocasting in, for example, PyTorch, then our data formats gets chosen like automatically. But it's a simple example. If we have FP32s and Tensor cores support TF32s, that's more efficient. It has a range of FP32, but precision of FP16. That's kind of enough. And yeah, another format is bfloat 16. That's also kind of a mixture between them. And in many cases, when some operations are better to be run in one precision, others in another, like, for example, batch norm, when we compute the statistics, we want to have a higher precision than if I just do matrix-matrix multiplication. But again, these things will be done automatically if you use like NGC containers provided by NVIDIA and you use autocasting functionality of PyTorch. It will do this kind of transfers automatically. So you even don't need to think which data format you're using. It's a simple example on how to use it. So we see on the right, I need to create a gradient scalar. And then when I have my, let's say, forward pass, when I compute my loss, I need to call this torch AMP autocast. Inside it, do compute. It's not recommended to do backward pass. It's better to do it outside. So now outside, I need to do this backward, but I need to be aware of the scalar. So that's why we don't use just like loss backward or optimizer step. We need to use three different functions, which is, again, quite easy to use. You just plug into your code, and your thing's going to be usually at least like 2x faster. You're going to use 2x less memory. So I think this is must-have for any deep learning training or inference if it's done in things like PyTorch. And so in order to understand if I use tensor cores, I can use profiling tools that Jason presented previously, or there is another profiler by Torch that I can kind of execute, and I'm going to see on the right if I use tensor cores. I believe you can even see data format and many other things there. So it can give you an idea. And yeah, I think ideally just after the presentation, look at the profiler in PyTorch. It's going to be much more documentations there. All right, so am I on the next slide? Yes. Another cool thing NVIDIA introduced with Ampere, it's Ampere sparsity. And it works the following way. If in my weight 2 out of 4 consecutive elements are zeros, then I can compress this matrix and send it to tensor core, where a compute going to become more efficient. Like in theory, your math gets exactly 2x faster, but because it requires this memory transfer for networks, for some of the networks, you will not see 2x. Like, for example, we see up to 30% in kind of research community. Again, if 30% is not what you want more, come talk to product managers. They will help you on that. Right, but this is Ampere sparsity is actually pretty simple to implement. There is also, it is a part of Apex libraries that NVIDIA provides. And there you can do pruning just by magnitude. So small weights get pruned, 2 smallest out of 4 get pruned. And then for some networks, as we have evoked this CVPR about transformer pruning, it happens that you don't even need to do any fine tuning. So you just apply Ampere sparsity into vision transformer, and you're gonna get like speed up of the model with no loss in accuracy. So no fine tuning is required. For some other networks, fine tuning is required. Cool. Now let's go to another set of tools or like aspects which we can look for to get higher efficiency. One of them is GPU memory, because we always want to have like bigger batch size, but it doesn't fit. So people buy GPUs with more memory. It's pretty awesome, but there is still a limit. Like for A100, we have 80 gigabytes at most. And so it really helps to look in what's going on there. So for model, like there are 4 basically different sections here. First is the model weights. If they are in FP32, I'm gonna have 4 bytes per basically every parameter. If I use a mixed precision, it's gonna be 6, because we will maintain model in two data formats. Next is optimizer state. So for example, for Adam V, because we store the first and second order kind of track statistics, I'm gonna use 8 bytes of memory per parameter. I can use a more optimized optimizers, like 8-bit Adam V or bits and bytes. And then I'm gonna use only 2 bytes per parameter. Or like just an example here that for SGD, because we only need to track momentum, I will use 4 bytes of memory. Now for gradient, it's gonna be always 4 bytes, because even in mixed precision, the gradients are still propagated in full precision, just to make sure that we are like not losing anything there. And usually for gradients, even very small numbers matter a lot for network training. And forward activations memory, of course, its primary depends on like parameters of my model. We don't have kind of much control once we fix them, once we choose them. So it's pretty important to also look at the memory aspect and to fit more. if we cannot fit everything into like single GPU training, then we can look into data and model parallelization. So in data parallelization that's very commonly used, we split our data. We send this data to different GPU workers, can be like even nodes or different GPUs in single node. And then they share the same model, they compute the gradients on their own data, and they exchange the gradients. So now all gradients being sent to like main machine, it's gonna average them and like transfer back the average gradients. And so this really helps a lot to increase the batch size during training, and very easy way to kind of have more, to utilize more GPUs without significant cost of communication. Another way of parallelization is model parallelization. So in case I cannot fit my entire model on a GPU, I need to think of ways to deal with it. And model parallelization is kind of one of them that's widely used. It is by itself divided kind of into two subgroups. First is pipeline parallelization, where one part of the network runs on one GPU or multiple GPUs. And then let's say the second half of the network runs on another part, another set of GPUs. And next model parallelization type is tensor parallelization, which I think is more efficient. So this is when you split your layers into different GPUs. So for example, if you want to train large language models, it might be that we cannot just fit entire even linear layer into GPU. So we need to kind of split them into different GPUs. This is going to involve communication, because once this gem is computed, I need to move them back so that for next layer, network will be ready to compute it correctly. So it's, I think the model architecture gonna determine which way of parallelization you wanna do here. Next step, how to make things more efficient during training is gradient accumulation. So if I want to train with bigger batch size, but I don't have many GPUs to run data parallelization, I can do gradient accumulation. So what it does, it's we give in a mini batch, we compute the gradient, and then we store the gradient. Then we go to another mini batch, we compute the gradient, and we sum it up with the previous kind of gradient I have computed. So it gets pretty efficient. I'm paying the cost of storing these gradients in memory, which is actually one cool way to even solve this is to move my gradients into CPU once I computed them. So I will not then use more GPU just for this particular gradient accumulation thing. Gradient accumulation is actually also pretty simple and straightforward to implement in PyTorch. So by default, we always do this optimizer 0grad, and it will go through all the parameters and put the gradient to 0. If I don't do 0grad, then with every loss backward, it will go and add the gradient value of particular batch into previous attribute stored of the weight with the gradient. So what I mean here is that we don't really need to do much. We just call loss backward and it will do this accumulation for us, such that after particular, let's say, number of iterations or something, I can do my step, which is, should be actually, the order should be reversed here. But yeah, so we will fix it. And another trick we can do is activation recomputation. So in the very simple example, when I run forward and I want to do backward, I will have to store all of my activations for layers to support backpropagation. So that's shown here, right? I will need to store all of these activations. It's going to take a lot of memory, such that on a backward pass, I'm going to do a backward of one layer at a time. Once I backpropagated through the layer, I can drop and forget about particular activations, but still I'm going to at some point store all of them. To make it more efficient, we can do activation recomputation or gradient checkpointing. So activation recomputation means that I will pay the cost of doing multiple forward passes but by using less memory. So if I want to do a backward for one layer, I will only store the gradients and activations for previous layer. I will recompute every time. So it is pretty expensive on compute, but again, sometimes we have to do it to fit bigger models. One way to speed it up is to use gradient checkpointing. Is when I'm gonna, it should be animation, yeah. When I'm gonna checkpoint my activations at some point, like here's the third node here. And so then when I'm gonna do a backward pass, I will always need to recompute my activations from this layer onward when I'm gonna do the backward. So another trick to train bigger models with limited capacity of GPUs. And of course, by this approach and gradient accumulation, you don't pay anything in terms of the accuracy. So it's just like smart algorithms, how to do training, but your training actually doesn't change. And it's particularly with this activation recomputation thing, you can think of some trade-off. So for example, on which layer to do checkpointing, you can decide, like basically looking at your model or running it and understand if you want to do some memory saving, but how much compute can you give to it? Cool, we are getting closer to presentation and to coffee break. Final recommendations. I mean, it's not really final, so everything I told before still makes sense, but this is just a kind of offset we have prepared. So first one, use automatic mix precision is gonna help you with doing more compute, and you don't need to do anything by hand there. It's just like 3 lines of code. Use gradient checkpointing, and this makes a lot of sense for large language models. Do empty CUDA cache. Sometimes it doesn't happen automatically. Same for garbage collector in Python. Sync and enable, if you can, lower optimizers that take lower number of bits, or basically memory. Another very interesting simple trick, I guess everybody of you know. So if I have convolutional layer and the next layer is a batch norm will kind of remove the constant factor of my data. So having bias in convolutional layer just is irrelevant. You whatever bias value you're gonna have, batch norm gonna cancel it. So that's why when you know that next layer is batch norm, just remove the bias of conv. You're gonna save memory and a bit of compute. Gradient accumulation, as we talked about, to have a bigger batch size for your updates. Some magic numbers that make things divisible by 8 for different formats can be 16, 32, or the higher this number is, the better, as we saw with you. Implement parallelization, data model pipeline. We talked about that sometimes you cannot just do with a limited number of GPUs. If you can, also offload tensors to CPU, and this makes sense, for example, for gradient checkpointing when you move there, or it can be even gradient accumulation, or very obvious example, exponential moving average that we use with many network trainings. You can just offload the entire model weights into CPU, because I don't really use that model for forward pass, right? I just track my weights with exponential moving average. So if you can also overlap compute and communication, and this is kind of what data loaders are doing. Data loaders you run them on CPU, they try to prepare data while you're doing heavy GPU compute, right? And this is pretty important to reduce time of the entire system. Same for data loader, use fuse kernels. For example, in Apex library, there is support for multiple optimizers that are fused, and you don't really have to write custom CUDA unless you want to do it. Another thing is about LoRa. I think it's getting very popular for large language models. If you don't have enough compute to do fine tuning of your language model, then you use LoRa, and that's things are going to be easier. Another example of about the trade-off, or how can I reduce like speed and memory for different techniques. Gradient accumulation, we saw that it really doesn't speed up things, but you can use it if you have limited memory. Same for gradient checkpointing. For mixed precision, you are getting a faster forward and backward with almost like very little memory cost. For batch size, of course, the bigger the batch size, a lower throughput gonna be, and also you're gonna use more memory. Optimizer choice matters. Simple example, SGD versus Atom. Data loaders, more efficiently you do them, your speed gonna be improved. Memory, not much on GPU because we don't have usually data loaders there. Some important cuDNN flags, how to make things faster. Because like all of the frameworks use cuDNN as a backend to do all the compute there. So few examples here. First is, of course, enabling cuDNN. By default, it's enabled, it's true. Allow automatic usage of TF32 data format. You remember that's something that between FP32 and FP16. Next one is determinism. So, and this is pretty interesting, that the way the splitting is going on GPU, sometimes you will have slightly different output of the same, let's say, model inference. If you want your, but this is going to be faster. So if you want your things to be fully deterministic, then you need to change this flag to true, and you will see your compute, like your model gonna take a bit more to do the forward pass. One more very important flag is a benchmark. So we want to enable benchmarking, which by default is disabled. And when you enable benchmark, for example, there are multiple ways to implement convolution operator, like through the FFT or Vinograd algorithm. And so in this case, cuDNN will do this for you. It will run a quick benchmark. So your first iteration is going to be slower because it will try multiple algorithms. But once it tries it and sees that, okay, for this particular layer, algorithm number 3 is the fastest, all the next iteration is going to be faster for your model. And one interesting example that we used, like many ideas from this presentation when we were designing next generation Vision VIT, is just recently been made available online. And so it provides like it provides the best kind of trade-off between accuracy and throughput. In this case, it's for ImageNet when we don't train with any additional data. So it clearly has a better accuracy at the same throughput number. So what I want to say here is that, like, if you use these guidelines, then you can easily just design more efficient networks or get this trade-off at the next level. Next thing is that if you care for inference, you have to use TensorRT. And in many cases, it's very simple to use. You export your model into, let's say, Onyx format, and then you run through even command line TensorRT. It's going to take some time to compile because it's going to check all of the possible things about fusion, about which algorithm to use for particular layers. But after it's going to do all of that, you will see things are getting significantly faster, like 2-3 times you can easily get with TensorRT for the same kind of, for the same precision. Of course, if you do quantize, you will get even more. And TensorRT has a simple technique to do quantization through like entropy. But yeah, I'm sure there are much more advanced techniques at CVPR for quantization. I think that's it. I'm right at 45 minutes. Thank you all for listening. We will make slides available so you can use all of these tricks. NVIDIA has a lot of documentation which I followed, shown here. There is definitely much more stuff if you want to learn about it. Yeah, that's going to be it. Thank you so much.
So we have time for a few questions if you want. This should be the time for the break, and we should reconvene like around in 10 minutes now. But I think if anyone wants to ask some questions, maybe Pablo can answer, right? So
yeah, well, during like right now, just come coffee break.
I'm going there. Just a quick question around the channel loss format. So I've tried out.
okay, welcome back. And I think in the interest of time, we're going to start with this afternoon session where we're going to talk about more like algorithmic improvements that we can do for model compression and for dealing with transformers and be as efficient as possible. And in the first part of the afternoon, Mayin Shen is going to talk about model compression and what are the latest advances that we are working on. Mayin has been with us as a research engineer for about 3 years, focusing on efficiency. She has been publishing on how to get the best latency out of your models. And for those who are here, at the end of the day, or at the end of the presentation, she will show how you can actually bring the advances that is presenting into the Jetson Nano platform that is staying here and showing some object detection live demo. Please welcome in.
Okay, thanks, Jose. Hi, everyone. I'm Mayin. I have been working on efficiency since I joined NVIDIA. And in this part of the tutorial, I'm going to share with you like how we can improve the efficiency through the neural network compression. So nowadays, when we are given a task to deal with using the neural network, actually, it is typically easy for us to get a large resource to train our large model with gigantic capacity. But it could be possible that the device that you really want to deploy the model on could be a very small one. It could be a small edge device like this Nano with limited memory and limited compute, for example. And you may just want to speed up your model to get a real-time inference speed feedback or a faster cloud service. And this is when you may want to consider the compression here. And for this part, I will show you like more particularly like for the compression, I will first introduce how we can quantize our model. So for the quantization, it is a light compression technique, which is trying to convert the model into a different representation in bits. And then I'm going to show you how we can prune the model, which would be a more aggressive compression technique that modify the model topology. And after that, I will quickly go through some tools that we can directly use for compression. Lastly, we will go through with you a live demo. So let's start with the quantization. So now, when we train the model, we typically just train it in FP32 to take advantage of the wide range of numbers so that we can improve the precision. And sometimes we may use FP16, but actually with the model saved in floats, we can further reduce the precision to make sure that we can further reduce the compute, memory, and power. For example, if we convert from FP32 to int8 with the support of the NVIDIA Tensor Cores, we can get around like 4 times a memory reduction and around maybe up to 4 times throughput improvement. But notice that the FP32 can represent around 4 million values, but the int8 can only represent 256 values. So there will be some precision loss when we do this kind of conversion. And we do need a mapping process to help us convert the data from the high precision to the low precision. And typically, we can use a scale factor, for example, to help us to scale the data from the original precision to the target precision that we want to use. And to be more generic, when we talk about the quantization, the goal we want to achieve is to minimize the loss between the weight before and after the conversion. And it does not necessarily to be the int8 quantization. Actually, it could be any codebook that you would like to use. And the ultimate goal is to assign to get the optimal assignment for each value that we wanted to quantize. And there are many different ways that we can use to optimize for this equation. For example, a couple of years ago, we had the work to work on the optimal quantization idea, where with a fixed code book, we optimize the scale factor alpha and its assignment iteratively. And actually, if we get a final scale factor fixed, it is quite easy for us to get the optimal assignment. For example, here in this figure, we have the original value and we have the scale factor, so we can get the value after scaling. Then we can just assign the value to the closest code value that is close to the data after scaling. And I think like among all of the code books, the int8 quantization might be the most popular because we can easily get the speed up from the support of the GPUs, and we do not lose too much on the accuracy. So with the basic idea of the quantization in mind, how can we really quantize our model? One way we can do here is to use the post-training quantization. As the name suggested, the quantization will be applied onto a already trained model. So with the model saved in the flows, we can easily get the distribution of the model weights so that we can apply the quantization algorithm to get the scale factor and quantize the weights accordingly. But at the same time, we may also want to quantize the activation, the inputs. So in this case, we need to collect some representative data to help us to collect the distribution of the inputs and the activations. And then following the same way, we can quantize the activations as well. So this would be a relatively simple way we can apply the quantization because we can directly use that onto any already trained model. But sometimes we may not be able to achieve the design accuracy. As I said, like after the conversion, we do have some precision loss here. So this is when you may want to consider the quantization-aware training. So the idea behind this is that if we introduce the quantization error during the training process, then the model tend to be adapted better to the quantized data. So what we can do here is to insert some fake quantization nodes. So we call it fake because we quantize the layer output and immediately dequantize it before we feed the output into the next layer, so that all the convolution operations and the weight updates will still be performed under the float precision, and we do not need to modify the training framework too much. And after the training is done, the optimal scale factor will be directly stored in the fake layer, and then we can directly use that to quantize our model and activation. So to summarize, using the model quantization technique can help us to save some compute and memory. And the post-training quantization might be more popular because it is easier to apply and there is no training process will be involved. But the quantization-aware training definitely will give us a better accuracy. Okay, so next part I'm going to talk about is the pruning. I'm going to discuss like what kind of categories that we have for the pruning and answer the question that how we can perform the pruning on a neural network, what kind of connections that we need to prune, and when we should perform the pruning. Finally, I will show you some applications and the results. So what is the pruning? Think about when you need to prune a tree, you typically just remove some useless branches from the tree. And when it comes to the neural network pruning, similarly, we are trying to find out what kind of connections would be useless for the accuracy so that we can remove them without harming the accuracy. And then you may ask like, why we not directly train a compact model, a smaller model? Well, actually like the larger model will typically be easier to train, and the over parameterization always gives us a better accuracy. And it turns out if we perform the pruning from a large model, then it usually gives us a better overall accuracy, better overall performance. And back to the pruning itself, pruning can be categorized into fine pruning and coarse pruning. For the fine pruning, we typically remove single parameters from the network, which will lead to some sparse metrics, and it will typically need the support of some specific GPUs or hardwares to get the actual acceleration. On the other hand, the coarse-grained pruning removes the entire channels, or sometimes we call it neuron pruning. So we can get a smaller model directly, and all of the off-the-shelf GPUs can benefit from that. For the fine pruning, as already introduced by Pavlo, like there is one particular case which we call the 2-to-4 ambient sparsity, where we follow some specific pattern, like out of every 4 parameters, we remove 2. And this kind of sparse matrix has already been supported by the NVIDIA ambient tensor cores, but like this is still needed the support of some specific architecture of the GPUs. And what might be more interesting is that we can perform the pruning on the channels so that all of the GPUs can take advantage of the acceleration. So in the rest part of the tutorial, I'm going to mostly focus on the channel pruning. But before I go into more technical details about the pruning algorithm, I would first to make a note here that when we do the coarse pruning, we need to carefully deal with the element-wise operations, because this kind of operations typically take the input from different layers. And when we perform the pruning on this kind of structure, we may want to make sure that the layers connected to the operation will be aligned in pruning. For example, we can make sure that the channels with the same index from different layers to be grouped together and prune them together. Otherwise, as I showed in the middle figure here, some of the layers after the element-wise operation might still be active. So which might not be the case that we wanted to have. Okay, let's move to the pruning algorithm. So in the literature, we can, the methods can be categorized into regularization-based method and the saliency-based method. For the regularization-based method, it typically encourages the sparsity during the training process by using some regularization items, for example, the group lasso penalty. So the training will be compression aware, and at the end of the training, some of the parameters or the neurons will be directly set to 0. Then for the saliency-based method, on the other hand, it typically takes a pre-trained model, and we are trying to find what kind of subnetwork will be the optimal so that we can get the best accuracy. I will cover this with more details later. And let's talk about the regularization-based method first. So this is the object functions that we typically use when we train a model. We always use a weight decay item to help prevent the weights to grow too large. And this is actually consider each parameter independently, trying to push each single parameter towards 0. But when we want to perform the pruning or perform the channel pruning, what we can do here is to add an regularization item, trying to encourage the group sparsity, where we put the parameters from the same channel to be in a same group, and then we can encourage them to be pushed towards 0 at the same time. So at the end of the training, if we apply this regularization item, then we can get the network with some of the channels to be set to 0. And sometimes we may still want to keep the single parameter sparsity. And then we can modify the regularization to be a combination between the lasso and the group lasso. And notice that if we decay the alpha to be 0, then this comes back to the previous regularization item where we only perform the channel pruning. So this is just one classic method that we apply for the regularization-based pruning. There are actually many different kinds of regularization items that we can apply to encourage the sparsity, such as the low rank regularization, the L0. I will not cover them all in this tutorial because of the limited time, but I think like this would be some representative methods that I will refer you to if you are interested in this kind of method. And I'm going to introduce more about the saliency-based method, which is quite common in the recent literatures. So as I previously quickly mentioned, this kind of method typically takes a pre-trained model as an input and then trying to find out the connections that will be less harmful to the accuracy. And we typically apply the iterative steps to perform the pruning. Basically, we apply some metrics to estimate the importance of the neurons, and then we rank the neurons according to the value, and then take the least ranked ones. And then the prune structure can be fine-tuned for a few of iterations, and then we repeat the steps again until we meet some stopping criteria. So you may also have already noticed that the most important part here is that how can we measure the importance of a neuron? The most intuitive way that you can do is to apply the magnitude-based criterion with the intuition that if the parameter has a low magnitude, then it tends to have a smaller contribution to the output. So it tends to have a lower accuracy, importance to the accuracy. Another thread of the method would be based on the gradient-based criterion, which stems from the idea of optimal brain damage and surging. And in this method, we directly estimate the importance, trying to see how much the loss would change if we remove a parameter. So it has been proved that the gradient-based method is performing better than the magnitude-based method. So I'm going to talk a little bit more about one of the gradient-based methods, the Taylor importance here. For Taylor importance in this kind of method, we estimate the importance by the loss change after setting a parameter to be 0. And this kind of process can be regarded as to add some perturbations to the existing weights. So the importance then can be estimated in the vicinity of the weights by the Taylor expansion. And if we take the first order Taylor expansion, the importance can be calculated from the model weights and the gradients, which could be easily obtained during the training or fine-tuning process. If we go to the second order Taylor expansion, then this goes to the idea of the optimal brain surgery, where we use the Henshaw matrix to estimate the importance. So, but the Henshaw matrix is typically quite hard to calculate. It might need to have more computation cost. And as I will show later, actually in practice, when we perform the pruning on our own model, the first Taylor importance may be already enough to deliver some promising results. Yes, the importance score that I just discussed is calculated on the single parameter. When it goes to the channel pruning, the importance of the channel can be simply estimated by the joint importance of the parameters. And if there is a batchimization layer following, then we can directly compute the importance on the batchimization layer, because the output will finally be scaled by the batchimization layer, right? Okay, here we show how the loss would change if we apply the pruning under different kind of importance criterion. And you can see here there is a green line at the bottom. Can you see my mouse? Oh, yes, so here we have the green line here. This is the Oracle result, which would be the best performance that we can achieve. And then from this figure, we can see the magnitude-based method, which is colored by pink, is actually having the loss increase when quickly, and even perform similar to the random pruning when it goes to when there is more neurons to be pruned. And here the red line and the purple line are the results using the Taylor importance with the first order and the second order respectively. And they are, we can see that they are almost close to the oracle. And indeed, the second Taylor importance gives us better accuracy, but like the first Taylor importance also delivers promising results, especially when the pruning is in a small ratio. So in practice, when we perform the pruning on our own model, it might not be necessary to use the second order Taylor importance to calculate the Henshu matrix. Okay, now let's recap again our goal to get the compact model. So you may want to fit the model onto a small device with the limited storage or memory, or you may want to improve, to reduce the compute or the power. This might be easier to achieve because the memory will definitely linearly decrease when you prune some parameters or neurons out. But think about the particular case where we have a real-time system with the hardware limitations. We may want to focus more on the latency itself and assuming that there is enough memory in our system. In this kind of case, we would like to maximize the compute capacity and reduce the inference time as much as we can. And to study this kind of problem, we first analyze how the latency of a layer would change if we change its input and output channel numbers. So here we plot the latency of the layer by changing the channel number. And you can see that actually the latency on a real device is not linearly correlated to the number of parameters or the flops. It turns to be a staircase pattern, for example. And different GPUs have different kind of patterns. So if we just apply some generic pruning, it is highly likely that we are not maximizing the compute capacity and the latency is not optimized. To optimize the latency, we tried to formulate this pruning problem to be a constraint problem where we minimize the task loss under a certain latency constraint. And as I just mentioned, like we can use the importance score to measure how much loss would change if we perform the pruning. So this problem can be naturally converted into maximizing the importance score of the remaining channels while still under the latency. And we use a pre-profiled latency lookup table to characterize the latency on the device and then incorporate that into our pruning process so that we can use that to guide our pruning. And the final, this will definitely lead us to a better overall trade-off between the accuracy and the latency. Here is an example from Resident 50 about like a layer from the Resident 50 after the pruning. And you can see that if we apply the latency-aware pruning, we can get a lower latency compared to the generic pruning, but at the same time, we are keeping more parameters in the layer, which means that it could potentially give us better accuracy. So this shows that by applying the latency-aware pruning, the model can tend to have a better overall performance. At the same time, when we perform the pruning doing the experiment, we empirically find that the aggressive pruning tends to give us a large accuracy drop. And this might be partially because that we are applying the first Taylor importance score. And as I showed earlier, like if we go to the aggressive pruning using the Henshu matrix to estimate the importance might give us better accuracy. But this also basically suggests that the pruning algorithm at some point is making some suboptimal selections. So what we propose here is to use a soft pruning technique. Instead of zeroing the pruned weights permanently, we apply the mask to the weights and make sure that the weights of the pruned neurons still existing in the model. And at some point, we can allow the pruned channels to grow back if it is necessary to undo some early decisions. Also, if we want to make sure that the pruned neurons can still receive some gradients during the following steps, we can switch to the input channel pruning, because in the modern architectures, the layers like ReLU will be commonly applied. So if there is a ReLU, for example, then the channels with the 0 output will just receive 0 or undefined gradient. So the width of the pruned channels might not be able to be updated. In this case, we can switch to input channel and apply the soft mask here. Here we show how the performance of the latency-aware pruning performs. Like we show the top one accuracy versus the inference FPS here in the figure. So it is clear that by applying the latency-aware pruning, it performs better than the generic pruning. And if we apply the algorithm improvement using the soft masking, we can get even better accuracy when it goes to aggressive pruning rates. Okay, so far now, like, except the regularization-based method, which could be definitely happen during the training process, all the saliency-based method we have been talked about just accept the pre-trained model as the input. So we naturally have this question like, do we really need to wait the model to be fully converged before we apply the pruning on it? And can we also benefit the training efficiency from the pruning? With this question, we studied the problem when we can perform the pruning without harming the accuracy. So instead of following the standard pipeline, like we perform the train and prune following the fine tuning, some of the works trying to perform the pruning at initialization. This will require the least training cost, but as many other works also pointed out, like this method tends to suffer noticeable accuracy drop, especially it goes to the channel pruning case. So one trade-off that we can have here is to perform the pruning during the training process as the regularization-based method, but we can try to push the pruning towards the early stage of the training so that we can reduce the training cost as much as possible. But the point to perform the pruning might be very critical. So we had the extensive result to show how the accuracy would change if we perform the pruning at a different stage of the training. It turns out that the early stage has a very rapid motion in learning and is very critical to the final accuracy. So if we perform the pruning too early, as the top figure shows here, we tend to get a very low accuracy. But at the same time, we also find that there is a stable dominant subnetwork appeared in the early stage of the training. And once that subnetwork appears, we can apply the pruning without harming the accuracy too much. To measure the stability of such a kind of subnetwork, we propose an indicator basically trying to measure the topology similarity between the current subnetwork and the previous ones. And it has shown that this indicator is quite effective. So when we apply the indicator to automatically decide when we should perform the pruning, compared to some heuristic settings like pruning at initialization or at some fixed point like epoch 30, the proposed method can give us more flops, training flops reduction and actual training speed up. And then another thing that I wanted to point it out here is that counterintuitively, pruning at initialization does not necessarily give us a faster training, because we find that the importance calculated on the untrained model easily lead to a slow network, where the pruning mostly happens in the late layers. So there is no much computation in the late layers. So, so I think like this is a quite interesting finding in this work. The pruning at initialization doesn't only impact the accuracy, but also impact the structure of the pruned network. Okay, we have shown some results on the classification task. Then let's go to the detection. Here, I'm going to show you an application of the real-time 3D detection for autonomous vehicle. This is the pipeline that we applied in our experiment. Basically, the model takes the input from two front cameras, two rear cameras, and 4 fisheye cameras. And then we extract the feature map for each camera image independently. Then we convert the feature map from the 2D space to the bird's eye view space using the lifting module. Then at the BEV space, we aggregate the feature maps and use a shared backbone to get the output on the 3D space. We use 3 different kinds of architectures for the experiment. The first one is a compact model, which is obtained using the architecture search. The other 2 are the Resident 18 and the Resident 50. So as expected, the larger the model is, the higher accuracy we can get, but the larger latency we will have to use for the inference. And it is clear, like from the figure we can see, by pruning from a larger model, it gives us a better overall performance. For example, here, when we perform the pruning on the Resident 50, it forms the frontier of the performance curve in the figure. So again, if you want to have a good overall performance of your model, we would suggest that we first optimize the accuracy first, trying to train a larger model, and then compress that aggressively to meet some certain requirement. That would potentially gives you a better performance. And when the original model structure is a very deep network, then layer pruning might need to be considered to make sure that we can reduce some data movement from different layers so that we can benefit the latency more. Here are some result comparison, detection result comparison visually. So on the right side is the result using a large model and then perform the pruning. The left part is the compact model. So we can see like the right one is delivering a better detection, especially for the large close objects and the far away and distant tiny objects. Okay, so one last topic about the pruning I want to discuss is the robustness. Think about that you now have a camera installed in the real system. For example, on the autonomous vehicle. And it is highly possible that the image captured by the camera would be corrupted by the natural noises. So it is very critical that our model can constantly deliver some promising results even under this kind of out of distribution data. Unfortunately, there will be no corruption known during the training or fine-tuning process, and we find that the pruning tends to harm the generalization ability of the model. So how can we jointly address the compactness of the model and the robustness of the model might be a problem. In our recent work, we are trying to encourage the compactness of the model and the robustness of the model at the same time. So typically for a model, it will be more robust if the solution of the model lies to a flatter loss landscape, because the loss would be changed smaller if there is some perturbations. So inspired by this idea, we encourage the model to let the neurons to be pruned, or those least important neurons to go to a flatter minimum. And after pruning, we encourage the robustness of the remaining channels to reduce the loss sensitivity to the perturbations. We had some preliminary results. And as you can see here from the figure, without encouraging the robustness, the model obtained using the latency-aware pruning tends to get low accuracy on the corrupted data. But with the proposed method, we can reduce the performance degradation and improve the robustness. So now, if you want to compress your own model, here are some tools that you can directly use to make your life easier. For the quantization, you can use the PyTorch code base to quantize your model, both for post-training quantization or quantization-aware training. And for your TensorFlow models, NVIDIA provides the toolkit with detailed user guide and example code. For the pruning, PyTorch pruning provides some basic pruning methods and also an interface for you to implement your own algorithm. And NVIDIA ASP codebase provides the solution for the 224 NPM sparsity. For the rest of the specific pruning algorithm I mentioned in the tutorial, we provide the link to our codebase for your reference. Okay, finally here we are having this live demo, and a special thanks to one of our co-author, Lei, who is not here, but put a lot of effort to make this happen. So we have a Jetson O-ring board here, which has a GPU and 2 DOA modules installed inside. As Jason also mentioned, like the DOA is an accelerator targeted for the deep learning operations that we can take advantage to get some extra compute. So let me show you how we can get the inference speed up by compressing the model. Thanks. Yeah, so here we have the original model. This is a SSD model, which is trained on the Pascal VOC. So it's not a very powerful model, but I can go in front of the camera to show you this is indeed a live demo. Yeah, so you can see here, I'm shaking my hand, moving towards the camera. Yeah, so this is a really live demo. Yeah, and you can notice that this FPS inference FPS is around 22, and we get the latency at around 45. Then I'm going to show you the model after compression. Yeah, so this would be the model after the compression. And let's see how the latency and FPS would change. Yeah, you can see like the FPS already goes to 40, right? And notice that we have the GPU load and the DOA load here, and you can see that the DOA is definitely being used to give us more compute. Yeah, so basically that's it. I think that would be the end of my presentation, and yeah.
We have time for some questions, if any.
Like we see that the DLA and GPU both are being utilized. So how is that workload being split here, and and how does the quantization or pruning affect this split?
Okay, so yeah, so I think like here you can see there is GPU 0, DOA 0, and the DOA 1. And we just load the model onto the DOA 0. And the DOA is actually a fixed function accelerator. So that is some operation specific. There are some certain operations will not be supported by the DOA. For example, the transpose. but the convolution will definitely be supported by the DOA. So when we load the model onto the board and enable the DOA, then the board itself will deal with the operations that will be supported by the DOA and use that to deal with the operations. All the remaining part will still remain on the GPU. And for example, here we have all the displays, things like that. Those will be still remain in the GPU, yeah.
Thank you.
Thanks.
Thanks for the great presentation. So I got a technical question about your first work, the saliency aware pruning.
Yeah.
So you mentioned you used the lookup table to prune aware of the latency.
Yeah.
Yeah, but like previously, Pablo had mentioned due to the wave and the tile quantization, so like pruning some channels is not always good.
Yeah.
So like, does your like lookup table always like include some details like some channels, number of channels is good, some are not?
Yeah, this really depends on the granularity of your lookup table, and to get a good or optimal performance, we will definitely want to profile all the possibilities of the input and output channel combinations. And here in our experiment, we basically just try to profile for like every eight channels. So yeah, the more fine-grained it is, the better the performance will be, because yeah, this will be definitely just guided by the lookup table.
All right, thank you.
Great, thanks.
Hey, hello. I have one more industry part problem. So say if we have the Orin platform and we want to do the BV like detection, say in this way we have like a 8 megapixel input for 8 cameras, and we have 3 backbones together with like a 6-layer transformer and then some heads. So what's your recommendation in terms of pruning and quantization? What's the best recipe?
That is a great question. And I think it would be an overall system optimization, actually. So the part that I covered mostly targeted for the convolution pruning. And Danny later will cover more about the transformers. But generally, I would see like pruning and quantization will definitely be needed to get your model faster. But I think that's basically what I can answer. Is there anything? Yeah, Danny, you can see something about it.
I can chime in my next section of the talk. So basically, convolutional neural networks as well as transformer, they have different properties. They also have different characteristics. So I was playing, how different methods scale from CNN to transformers. And I think the question you answer is very interesting. And I hope the talk next will bring some insights there.
Great.
There are a lot of redundancy of different spectrums.
Yeah. Looking forward.
Sorry, the person before asked the exact same question I was going to ask.
Okay. Great, thank you.
So there's one last question, I think, is how do you compute the latency on CPU, GPU, or on edge devices like an iPhone?
Oh, basically, I think this would be a question like how we can get the latency lookup table, I think. So what we do is that for each layer from the network, we get all the possibilities of the combinations of the input and output channels with some specific granularity. And then we get that, get a layer saved, maybe in Onyx or in the PyTorch. And then we pass that onto the device that we really want to use and profile the latency and keep that into the table. So I think that is what we do. Yeah.
Thank you. There's any other question? I think online there's some questions, Pablo, but they're addressing the iPhone part, right? Yeah. In the compatibility with iPhone engines. Anyway, thank you again, Mayin. Excellent.
Thank you.
You're gonna switch. So last but not least, Danny now is going to cover the recent trends in transformers and scalability of these techniques to accelerate and be more efficient with more modern architectures. Danny has been a research scientist, senior research scientist at NVIDIA for a couple of years now, and he has been working on the efficiency both from the model and from the data point of view. And today we'll talk about that side, also about data privacy and some other considerations that we may want to take into account. Please welcome Danny.
So good afternoon, everyone. My name is Hongshu In. You can call me Danny. I'm a senior scientist at NVIDIA Research. And today I will give a talk on towards efficient as well as reliable deep learning, mostly from a research point of view, since it's CVPR. And I hope, the topics or the findings we're gonna, cover in this talk will inspire, new ideas as well as discussions that will follow. And I want to emphasize whatever techniques we're gonna show here has been, we verified on GPU, so they are really GPU friendly. So feel free to apply them in your future research projects or industrial projects. And at the end of the talk, I will include all the source code, like open source links that you guys can try on the different research papers. I will not put too much time here on emphasize the importance of, efficiency as well as reliability of deep learning models, because now it's really getting pervasive usage. So especially we are entering in the new realm of multimodality, GPT-4, like large language models, and we have to run them, all at different places. Sometimes it's self-driving cars, we have to run it on the cloud. And oftentimes we also need to face extremely stringent latency or memory consumption constraints, such as on the mobile phone. And hopefully this talk will give us some kind of intuition that we have been believing, which is making network reliable as well as efficient really boils down to we want to understand these networks better. And the insights I want to cover is the more we study these two topics, neural networks really giving us more interesting insights as well as surprising capabilities that will, help us, how we can better use them as well as protect them. That is the end of the talk. This talk will be, not focusing on the techniques that we previously developed for CVIN, but more we want to show this change of paradigm, like that the community has been facing in the past 2 years. Where transformer is gradually catching up. Like it shows really amazing performances, not only for vision, but also for language, and nowadays multimodality. Talk will be computer vision focused, but the methods mostly will go to language model as well. So I don't want to put that constraints into here. And this is a high level overview of several of our recent work that I'm gonna touch upon today. I divided it into two major sections, and mainly I want to discuss, how these methods we developed previously for convolutional neural networks, how they scale to vision transformer as well as language models. And the more we focus on network efficiency, we really understand, networks are so strong. And towards the end of the talk, I will show, these networks learn so much such that it encodes a substantial amount of prior information. We can extract a lot of data from these models, and we can use those data freely for post-training optimization, such as pruning, quantization. Previously, we need access to original data set, but now, these models are so strong, we don't need it. And because they become so strong, we need to, in a way, protect them because they memorize or in a certain manner encode a lot of information of the data that is trained on. So hopefully, these kind of insights will offer some kind of future research guidance as well. I will start the talk on the previous efforts. So because it's research focused, so I have more freedom, to touch upon some other topics. Post-training optimization, in-training optimization, I think Mayin and Pablo, I think have covered these pretty well. So I will not spend too much time on pruning because it's really well studied. It's very easy to use and gives direct speed up on off-the-shelf NVIDIA GPU hardware. In this talk, I will target a little bit more advanced technique, which is just off the research phase that we found is very efficient, which is called latency-aware network adaptation, which is LANA for short. So we just published at ECCV last year. So LANA framework is slightly different from conventional pruning, neural architecture, search, quantization, because if you will look at those methods, right, they are very easy to use. It gives direct speed up of the pre-trained networks on the target platform, but in a way, it is still constrained with the original architecture. Let's say for pruning, you can only remove certain parts. For NAS, we design search space, but we still massage networks around the area. Quantization is still, we remove the precision into a lower quantized parts. It's sometimes computationally very expensive and sometimes hard to use. But what we want to now propose, which is a new paradigm, is offering more degree of freedom into this post-training model adaptation. So our hypothesis here is we just train one large network, and upon inference, we swap these networks into faster or security verified alternatives. Because we have this model that is already trained, so we don't want to disrupt it so much. It is very large, it achieves very high accuracy, but when we do inference, we really face lots of different platforms, different inference time constraints. For example, on GPU, CPU, accelerator, all these constraints, we need to modify this one quite frankly, often many times, such that it will accommodate all these constraints. So how are we gonna do that? We propose this 4-step methods. Basically, we reformulate this entire process as kind of like a legal type of search, which is combinatory problem. And the key insights is we use the pre-trained model, which is what we call this train one large model, and we use it as a teacher. So what we mean by teacher is we treat the entire network because it's layered by nature. We just find these very hardware or secure operation alternatives, which is specified by the candidate operation on the right. So the key approach is in order to satisfy, for example, one constraint, we need to just find a viable path from the input to the output that we use during the inference. So how are we going to do that? Selecting this path is infeasible if we don't have any clue or hints. So how we do that is we want to first use layer-wise distillation to prepare these operators such that these NAS approach is not done in a completely random manner. So this one is we just distill from each layer the input to the output such that these operators are kind of approximating the teacher cell level using completely different operators. So these operators can be, for example, different attention, different QKV. So basically anything that you can think of on your hardware that satisfy your hardware constraints, you can put them as new operator candidates. So once we do this layer-wise distillation, we have some kind of clue, for each layer, what is the latency benefits this operator will bring me, and what is the associated accuracy drop, which is specified by the distance between the distill operator versus the teacher. And these two metrics will give us a very simple combinatory task. For example, in order to satisfy the latency constraints, what is the minimum amount of accuracy loss we want to have when we combine all these different legal blocks? So this offers a very simple combinatorial problem. So it's solvable in CPU seconds, which means we just do one time of this layer-wise distillation. Any kind of latency targets, just do one quick search, it will give you a target path. So you can just do very quick fine-tuning. For example, 5 to 10% of original training recipe, it will give us a very reliable path for the final inference. So this was some time ago on efficient net results, where we just apply the methods to efficient nets and just modify the efficient net checkpoints. It basically dominates all the open source models that we observe on team library. And we measure it, this is the real throughput on our GPU. So, just modify these gigantic networks, it's very fast. It gives you entire curve, so no longer discrete checkpoints. So this tool is very easy to use on the CNN. Okay, so how about vision transformers? I think people are very interested in this topic right now. So we covered quantization, everything on Lana on CN. Now, basically, the biggest question we have here, right, is we have been working on the efficiency for CNNs for quite some time, and there are different methods. So how they scale basically to vision transformer, right? Because if you look at the VIT, the architecture, it's simple and complex. So for CNN, most likely we are dealing with a lot of filters that have this different shapes from input to output. But for vision transformers, this, even though it's simple, but it's different computation other than simple convolution, but the same type of blocks it is stacked, from the input to output. So it's slightly different, change in the realm, and how we can exploit the previous approaches we developed in CNN to make VITs fast. So I would cover 3 slightly different approaches to show how pruning scales, how adaptive inference scales, and how quantization scales. So in short, methods scale, but at small minor tweaks, and it will work pretty well. So NVIT is our, I cannot. Okay, I think I'll just leave the upper section there. But this is structural pruning. I think this is just a teaser of how the methods will work. There are some small tweaks that we need to do on the transformer because transformer have this head dimension and in the upper bound. But what we do is we need to reshape the tensor a little bit such that we can rank all the components together. But the short message is the previous saliency-based approach scales well across transformers as well. And the good benefits is it even allows us to prune, to consider all the parameters, for example, QKV projection, the 2 fully connected layers, across all the layers simultaneously, which is just one global importance ranking. It will do this global pruning all at once. And so this is a very recent paper we just published this year at CVPR, and there will be a poster associated with it. So if you are interested, come and discuss with us as well at the poster session. I think is Thursday morning. What we found interesting about this work is the pruning really gave indication of the importance. So previously, from NLP task, oftentimes people deploy the same transformer blocks, just repeated 12 times, and it's kind of working pretty well. But it can be also a very lazy or straightforward solution, right? So what we show here is pruning is in fact a very indicative methods for us to rethink the importance of these parameters such that we can distribute it in a better manner. And we just leverage pruning to analyze the trend and just throw away, some of the parameters towards those parts and redistribute towards the middle in the autoencoder shape. It directly gives much better parietal front in terms of accuracy throughput trade-off. For some quantitative results as insights, so we always focus on device measurements, not proxy. Also, we are interested in lossless compression. So this is on the DEIT checkpoints from Meta, where we improve, for example, the throughput by 90% without too much accuracy loss. We observe the sweet spot is around 2x compression for the current vision transformer on NVIDIA GPU. So that's some interesting fun as well. Another thing we found, which is consistent with Lana observation, is starting from a large, well-trained model and then accelerated it to smaller counterparts is beating those smaller counterparts when trained from scratch. So the high-level intuition is the large model allows us to train the models better because it has more degree of freedom during initial training. But after the model converges, using this post-training optimization allows us to quickly find small counterparts that dominate those small ones when trained from scratch. So if you see here, right, we will compress the base model to the speed of tiny and smaller variants. We observe quite sharp increase in the top point accuracy, which is more than 1% for that observation. We also observe for ampere sparsity, vision transformer is quite robust. So we can just apply ampere sparsity without any accuracy loss, without any fine tuning. These are some of the interesting insights when we analyze the post-pruned architecture. So remember previously all the 12 blocks or all the 24 blocks, they are the same dimension, same parameters. And when we analyze what's remaining, which is considered as more important, right? This surprising or interesting pattern emerged where we observe there's kind of implicit autoencoder within this pruned architecture. We observe the first and last layer, they are important. Like first layer dealt with input, last layer dealt with the classification loss. But in the middle, it really emerged, which was this kind of semi-autoencoder-like style. So we just use this method, just to use another scaling rule, which is don't use the same amount of computation. We're basically scaling on the most important parameter, which is we consider the embedding dimension. So this embedding dimension is also one of the key factor language model used to scale across different checkpoints. So we also base the scaling rule of vision transformer onto this embedding dimension, and it works pretty well. Like we just use this one method without any kind of rigorous fine tuning. It directly generates consistent improvements compared to just normal models trained from scratch. Okay, another perspective which is super interesting for transformer we observe is it offers a unique perspective for transformer other than CNN is adaptive inference. So if you, as humans, right, for us, we do computation different from neural networks. If we look at the tiger, for us, it's very easy to tell it's a tiger on the left, right? Versus that camouflage deer on the right. So because we're able to, process this information very differently according to the input context, but across neural networks, right? Oftentimes we throw, the networks will give the same amount of computation for all its inputs at all the times, which is not efficient and not correct. So are we able to deal with the problem? So adaptive inference or dynamic inference literature have been focusing on this task for some time for convolutional neural networks. And for CNN, it's a little bit trickier because the feature map dimension is changing, the amount of channels are changing, which means at different stages, we have to make this decision, differently. But for transformer, it offers us with a completely easy situation because as we look at this paradigm, right, transformer first cuts images into patches. And these patches, the information density or the importance of these patches vary by nature across different images. So how can we adaptively select this one? So this is the work we introduced last year as CVPR 2020, which is called AVIT, or Adaptive Tokens for Efficient Vision Transformer. So the idea is pretty simple. Actually, we just apply the previously proposed methods for adaptive computation graph from convolutional neural networks onto transformer, and the results are working like surprisingly well. So the key idea is we will let the transformer self-determine which token to keep and which token to throw away as the inference proceeds. So it has some rough estimates of the situation, and then it gradually throws away the backgrounds because it's no longer important for my downstream task. So we observed the network's very surprisingly good at this task, and this is only one of the approach. We use ACT. We also observe, for example, some proxy other work from the field, for example, dynamic VIT, people from Tsinghua, people using Gumbo softmax. But I would say all the insights converge where transformer is really able to focus quite effectively. And that offers some room, to basically throw away the redundancy from this new angle, which is not viable previously in convolutional neural networks. Because if you think convolution, it will always move to different positions all the time. So I think there is also one very recent paper from MIT. Basically, it tends the methods to BEV fusion as well. I think the previous question. So this may offer a new degree of freedom there as well. So they use L2, which is another simple importance ranking of the tokens. So I will not cover too technical details, but just offer high-level views. So this is the results we got when we do adaptive inference on ImageNet. This is validation set. So the whiter region means those transformer tokens are processed by deeper layers or by more layers. And the darker region means those tokens are, after a few layers, transformer just throw it away. So, entire training is without any human guidance. So it's just some kind of penalty towards efficiency. And we observe transformer self-focus on pretty informative regions. I put the original image on the left and the associated compute on the right. So you observe it's a very high correlation between the two. And interestingly, it also focuses on multiple objects here. And, it ignores this human predicts because ImageNet 1K doesn't have this human as labels. So when we just fine tune it, it learns that stuff. We at NVIDIA will care a lot on on-device speed up. So this method, through token dropping, it gives 40 to 60% throughput improvements, some slight accuracy drop. It works with off-the-shelf GPU, so we didn't change anything. That's another beauty of token dropping, because how transformer operates is when you drop the tokens, you don't need to modify anything. So just disregard some tokens, transformer will still process all the QKV projection, cross attention, anything after you embed them properly as well. Okay, then we come into how about low precision for transformers? So we touch upon pruning, touch upon dynamic inference. Lower precision, I think, is critical. It becomes even more important nowadays compared to previously. And for this part of the talk, I will in particular focus on large language models. And this is a very recent work with our colleagues at MIT that published at SCML 2023. So consider, right, our language model are really large, like it becomes more than 100 billion parameter range. And just not to mention about training, just doing inference with these models are very cumbersome. Like, let's say if we want to serve a 175 billion GPT-3 models, and just to do inference, if we do FP16, it will easily consume 5 GPUs just to do one forward pass. And if we're able to do it, for example, in int8, it saves a lot of resources, as well as saves us a lot of compute. But is it that simple? Because, you know, int8 or WA weight 8-bit activation 8-bit quantization, you know, has been an industrial standard for CNN. So we know for a long time, it's pretty reliable. We can just quantize the model into 8 bits. It will not give us a pain in the ass. But now this is no longer true for large language models. So if you look on the upper part, which is the model size when we scale up these large language models versus the corresponding performance, we indeed observe the conventional way of doing quantization is no longer working after 7 or 8 billion checkpoints, which means we need some kind of smarter way of doing that. And luckily, we found that way is not that sophisticated. And I will just show the motivation here. So if we take a closer look of where the pain is coming from for why these original quantization no longer working, it turns out the pain point is actually lying in the activation part. So the weight converges pretty well after we train the models, but the activation, which is the embedding, it really have these substantial outliers across this dimension. So it causes traditional quantization scheme to diverge very easily because these outliers are very large in magnitudes. If you look at the vertical axis there, but you know, one lucky spot is we observe it to really conform to the same channels, which means the outliers, they oftentimes exist in the same part where we can just rescale them. And this is the approach that is recently accepted from colleagues at MIT, which is called smooth quant. I will not touch upon all the math, but the high level intuition or the main idea is we want to directly scale down this activation a little bit and just throw the associated rescaling factor into the corresponding weights. So previously, activation is hard to quantize. Weight is very easy to quantize. Now it shifts into a new paradigm by just rescaling them. Activation is now easy. Weight is harder, but still easy because anyway, we want their final products, right? So just scaling these rules allows us to have the same final products, but different initial value range of these models. So it's a very simple but effective trick. And it now push int8 quantization, which is W8A8 towards the FP3016 level. So if we check the performance comparison here, the accuracy loss is pretty negligible. So this is published results. And we observe it is able to directly cut down on the computation cost, which is shown on the right. For example, we can now use 4 GPUs to run the associated jobs that is previously for 8 GPUs, or we can boost up the throughput by 2 just using these methods. Okay, I think I've covered a lot on model efficiency. So the more we understand these models, we are more surprised by how good they are. But when we want to do this post-training optimization, oftentimes we need to get the previous data. So we need it for fine-tuning. We need it for calibration, which is a pain, especially when data nowadays really become proprietary. So people will share discrete checkpoints. They will not share the data. So how we want to tackle that, right? And in this part of the talk, I want to basically show some of our earlier findings where networks are really strong encoding machines for the previous data set distribution. For example, this is what we published some time ago, which is 3 years ago. So basically shows on convolutional neural networks, it is able to, it encodes such amount of previous distribution such that we can just convert noise into images without any other guidance. So with this, we call it deep inversion, which is a model inversion approach. So the key idea is previously we train the networks giving natural images, but now since the network has learned a lot, right, we just freeze the network, but backpropagate the gradients onto the input. So how about we optimize input instead of train these networks? Because the networks has learned a lot, it needs to guide me from completely Gaussian noise into reasonable distribution, right? So this forms the motivation of the results we show previously. So these images, right? These are, we take off-the-shelf ResNet 50, pre-trained on ImageNet. So it's not a versatile train. It's not any kind of GAN style, which is normal discriminative ResNet 50. And we use it to convert Gaussian noise into ImageNet level synthesis at high resolution. This is 224. Which means, you know, networks encodes a lot. So it's class conditional. We just change the different output labels. It is able to give us lots of data here. These data are class conditional. It's very high resolution, high fidelity, and also high diversity here. So each horizontal axis I show here is basically one target class. We just specify the cross entropy ratio, a cross entropy label at the last layer, and let the network, you know, freely converge into different final points. And so this is how the optimization converts these pixel-wise random Gaussian into these natural images. I think, yes, yeah, so this is quite interesting. So because networks, they are trained, right? These trained checkpoints encode these data, and now we can use this data as if they are the original training data set. You know, we just use this data and we use this pre-trained model, and we can do a lot of amazing stuff. So this makes entire pruning data-free. So just give me a prune model. We can now just compress this model and fine-tune it from scratch without looking into the original data set. We can even use this, this method to train a new model from scratch, as I will show later. It also does pretty well. And we can also do it with continual learning, because for continual learning, there's a huge forgetting of the previous distribution. So we show the synthetic data just by doing model inversion is very easy to maintain that. So I would say for pruning, we observe very slight accuracy loss. It's not yet SOTA compared to if you have original ImageNet access, but it's substantially beat if you do not have any data at all. So we observe it outperforms some of the previous baseline when we use zero image and as well as zero label, which is a real. We just use synthetic images. It is able to do the fine-tuning job pretty well, which means without access original data, synthesize something, we are able to fine-tune the model and recover the performance in a decent manner. And these data can also support us to train a new model from scratch. So we basically want to make the situation a little bit more challenging. Just use these synthetic data to get a new model. Is it viable? So this is the answer. It seems the data set captures the original distribution pretty well with only 0.14K synthetic images. We are able to transfer the knowledge into a new student, which is the same architecture as the teacher. Here is a ResNet 50, trained from scratch on ImageNet, achieve 74% top-point accuracy, which means it captures the data set pretty well. And for continual learning, same situation, it outperforms the previous learning without forgetting by a quite substantial amount of margin, and approaches the oracle pretty well. Okay, so the key idea is, I think, feel free to interrupt me anytime, like with questions, but I don't want to go too fast, but the key idea is networks encode a lot of data set priors. So we can leverage this one to invert some data, to help with the downstream tasks. For example, quantization is also one that, other related groups from UC Berkeley, they also do zero quant using similar methods. But does that mean we have security indication? Because the most, we received many questions at that CVPR at 2020, basically, does network really learn of the concepts, or it memorizes stuff? So we took, several pokes around these fundamental questions a little bit more. And the answer turns out to be, I will not say yes or no, but I will show the results later to let the audience decide. Okay, so it seems we compare deep inversion images with the original images. It seems using normal Gaussian inversion, the invert out images are not identical to the previous data sets, which for sure the network is not memorizing, because especially when the network, when the amount of data really scale up, it's pretty hard for the nets to memorize. But it turns out there is a security bridge if we have some other proxy information of the training batch. So let's say if we have the associated feature map that is passed along with the original data, which is a common case in a split computing setup. For example, we have part of the network on the device, which can be a smartphone, and the main network on the cloud, which is the post processor, the main chunk of the analysis. And we just apply model inversion. With these feature maps, we are very confidently reconstruct even the pixel level details of the original training data. So if you look on the right, upper section is the original training data, and this part is the reconstruction. So it really gets a lot of details, even at a very high resolution for very deep neural networks. So we invert, for example, even up till the 42nd layers of the ResNet 50. It is still, process lots of information because previously conceived after many layers, these feature maps are filtered in a way it preserves only informative regions, but it turns out to be not the case. It even gets the entire pixel-wise details across the entire image. Not only feature maps, we also observe gradients are also not that secure. So gradient sharing is the central tenet between, for example, federated, collaborative, distributed learning. In this setup, people just share gradients. And the key arguments is we share gradients as proxy of original training data, but they are not training data. So multiple agents, we are able to jointly optimize a global model with the local gradients that we compute, but we never share local data. The field has been studying this problem for some time, but there are not yet a very successful attack yet on this problem. But it turns out for convolutional neural networks with model inversion, it is the case. So what I show here, right? Client is having this private data, and with this strong, because the network is so strong, it encodes all the data set prior and just get the gradients. And bear in mind, this gradients is averaged, which means the gradients from all these images are averaged together such that it will migrate some kind of per image information loss, but still the network is able to get back all these pixel level reconstruction. So this is the correspondence of the image level reconstruction. We observe in the paper, we just studied until like 48 batch size, but it gets us some kind of results as well. And this is the results we got from the attack on ResNet 50. So this is 2 years ago. We show it at CVPR. So this is a quick demo. Again, it's still, so we just give guidance onto the random noise. So basically we fix the target network and let it, just throw some gradients onto the input noise. And input is completely Gaussian noise, zero mean standard deviation. And the upper bound, the lower section is from the average gradients, the network is able to approximately guess the original image, and it gives us pretty high fidelity as well. So it works off the shelf networks. So networks are not adversarial trained, it's just normal networks. There's no GAN for synthesis and no metadata on this one. So for other domains, this is COVID-19. So one very essential situation for federated learning. COVID-19 is also, you know, a tragedy, but we just want to make sure with these insights, we can better protect how we do federated learning, especially in those kind of sensitive domains. Okay, now, how about vision transformer? So we understand, you know, CNN encode a lot of information, and vision transformer arguably are now catching up. So how they behave under this situation. So we just take one step of the challenge and offer insights here last year. So this is last year's CVPR. It turns out transformer is even stronger. So let me show the results here. This is the when we apply our previous most successful methods on VIT. So this is with some small tweaks of which is what we call GradVit, gradient inversion vision transformer. So this is the original image. It's also in a batch setup. We do batch size of 8, and this is the reconstruction. So if you look at, right, like vision transformer, just throw in some gradients, it is able to get back very, very high fidelity reconstruction compared to CNN counterparts. And it is even able to get back this entire person statue of the correct gesture at the correct position. Because, you know, for CNN anyway, we have this convolutional filters that is operating into this region. So it gets back some visual feature, but not all. But, you know, vision transformer, because of the patchification it does, it really gets the entire context pretty accurately. So observation hold, I will not touch upon on details, but, you know, some priors that we guide into this process, how it works for other sensitive domains. So this is a facial recognition vision transformer. Again, the tech's pretty successful. So the key idea is like, okay, these models are quite strong. So after we well-train these transformer models, better be careful what you want to share, as well as like this often, we hope also this tool will help us understand, you know, where the transformer focus on, right? Because it seems it is compared to CNN, where we observe it always focus on informative regions. It will just throw away the chunks of the background. But for vision transformer, it seems to treat everything everywhere consistently. So it really encodes a lot of information of the original training distribution. Okay, I think I would try to make time meet. So this is the key idea I want to show to the audience. Hope it offers some kind of insights when we move from a CNN realm to transformers. I didn't touch upon too much on CNN, but it's a Lana approach. But for vision transformer, what I want to say is pruning really scales well. It works. So mostly the methods we develop for CNN, it moves swiftly to transformers. Adaptive inference actually scales better. So previous headaches we have with CNN is now alleviated in a way to transformer because of their same architecture style at all the depths. Quantization skills as well, but with some minor tweaks. So we can apply it there as well. And because network's strong, so that second part, it tailored towards data efficiency as well as security. But that is what I want to include to inspire future research to basically help us understand a little bit more of these models, because they really, really become more stronger as the community moves forward. So because this is research part, oftentimes we will release all the source code as well as some data sets, training proprietary stuff at NV Labs. So this is also where we previously released Stelga and all the associated image generation contents. I included several of the links that feel free to try these SOTA methods. And actually we will continue to release more as more code is approved. Okay, thank you so much. And this is a joint work with a lot of your thoughts.
Thank you, Danny. We have time for some questions, if any.
Hi, yeah, thanks a lot for your talk. So I have a question on AVIT, the adaptive vision transformers, and they seem really exciting, especially because many examples are easy and some examples are hard. So you could throw out more tokens on easy examples and the model could learn this. But we learned earlier in the day that TensorRT kind of likes static inputs, static outputs, and like a fixed computation graph. So can you talk a little bit about how you would have like an adaptive model in TensorRT?
Yeah, I think I haven't. That's a great question. I haven't tackled too much technical details on the good thing, but token removal, that's the beauty of token removal, because token removal doesn't change the underlying graph configuration of the transformer block. So you can consider, you can just manipulate the intermediate tensor, which is the activation, just drop the tokens, reshape them, and just throw to the next transformer level. So it is very compatible for all the libraries. So basically we didn't change anything when we, for example, the kernels, the associated computation graph, because it's just token removal. So that's the, I would say, a benefits of transformer, because previously that's infeasible for CNN, because once you change the weight matrices, it's pretty challenging. But when you manipulate the activations, which are the tokens, it is a much easier task.
Oh, thanks.
Yeah.
I have just a quick question about what you showed before, so on Gradvit. So do you think that you were talking about the security concern and so on, but do you think also that you can distill new data directly from it, and eventually thinking about also quantization where training with less data that you have distilled from it, and then eventually doing this stage for a VAT kind of model done? Yeah,
I think that's a great suggestion. I mean, we didn't show in the slides, but data-free quantization is a very vibrant field. Like if you check 2020, there is 0Q from UC Berkeley. I think very recently, they also follow up on large language models, data-free quantization. It also works pretty well. So the key idea there is basically we can use inversion to get, for example, several quick templates that will give us the dynamic range very easily for the fine tuning. I think that's the key niche. I think, yeah, several work focused on that one, which is, I would say, working pretty well on the quantization scheme.
You said that with this gradient inversion and then you synthesize images, you can use this also for the data-free quantization and compression. You showed results for ImageNet, but did you try this also for other tasks, like, for example, 3D object detection?
Yes.
And so on. And what are your insights on that?
Yes, so that's a good question. So we do try it on object detector, which is SSD, I think. I didn't put it in these slides, but it's called Diode. I think it's at WACV 2021-22. So we didn't observe very high fidelity in the generated images from object detectors, but we do observe the synthesized images. They have the visual features. So we are able to tell it's a microwave, but it's a little bit funky. It's not yet very natural microwaves. I think it really boils down to what network learns, right? Because all this entire process is basically based on the underlying network. But the results is pretty promising for that paper that we show, because for knowledge distillation, either you have original data or you have some other data, right? But the other data we observe is sometimes have domain gap of the original data. So using synthetic data is better than you use other domain data. So that's the key insights we found there for object detection as well.
Okay, thank you.
Okay, so the question is, once a network has been trained and quantized and possibly pruned, would you think the network can be inverted so people can retrieve the private training images? That's a great question. We do observe there's a difference in the inversion efficacy across different checkpoints. For example, we observe self-supervised learn checkpoints. They are easier to be inverted. For example, MoCo models are easy to be attacked. Oftentimes, we also observe like large models, they encode more information. So this question, I think, really boils down to how pruning as well as quantization impacts the network strength, right? We don't have numerical numbers at the current stage, but it will be a very interesting research topic to explore. But what we had previously is, previous insights is, if you train the networks differently, if network strengths are different, they do have different behavior under the inversion attack.
Okay, thank you very much. This was probably the last question. Thank you, all the experts, and thank you all for you for staying here. One last comment. I mean, if you're interested, I think efficiency is a very important topic. So if you're interested, we may have some openings for full-time or interns. So please feel free to contact Pablo, myself, Mayin, or Danny, Jason, and we will move from there. Thank you all, and see you in the CVPR.